transformation, I have to interact with the electromagnetic field. So the electromagnetic interaction is introduced to have symmetry in the theory. Now, depending on the group of invariants, this new field may be Maxwellian, that is a mu, or maybe Yang-Mills in general, or higher order tensorial field. This is because this scalar theta can be written down as the dot product of two vectors, where omega is a constant and sigma is the Pauli matrices, sigma 1 I cap plus sigma 2 j cap plus sigma 3 k cap. And if I require invariance with respect to this sort of transformation, e to the power I theta of this kind, I will have to introduce interaction with the Yang-Mills field. So I will have to introduce Yang-Mills field. Similarly, I can write theta as it is a scalar, so I can have the tensors which can be contracted, and so 2 by 2 tensor contracted, so I can have others. So this is the general procedure. So you have to introduce interaction with new fields if you want to have the invariance. So this is now latest is the supersymmetry. What is supersymmetry? I will come back to optics slightly later, as Anurag asked me to do that. Supersymmetric transformation allow one.
Ajit, you have limited time. You have only 4 minutes. Okay.
Bolo?
You have only 2-3 minutes left. I mean, not much time. So just quickly.
नहीं कितना हो गया 50 पे शुरू किया चलो मैं फटाफट करता हूँ supersymmetry bosonic state transform into fermionic and vice versa. So the main property of supersymmetry, so again what I'm trying to do is, okay, I will skip this slide, come here. So now this Einstein actually what he did was he showed that symmetry dictates interaction, that to have symmetry you have the interactions which we see in nature are maybe the consequences that nature has certain symmetry, and that symmetry is realized through interactions. For example, general coordinate transformation, general relativity, abelian transformation, gauge transformation or symmetry gives you electromagnetism. Non-abelian gauge symmetry gives you Yang-Mills. Supersymmetry gives you theory of superbosonic and fermionic state. You can have supergravity, and then there is the question mark unified field theory or unit theory of everything. Nobody knows what symmetry this should be, in spite of the fact the string theory is there. Now, to relate to optics, let me quickly go through that there is something called CPT symmetry. This is the most fundamental type of symmetry in quantum field theory, which is where it does hold for all relativistically invariant systems obeying the causality principle. In reduced form, CP symmetry is almost exact to also too. So all these things are valid if you have Hermitian Hamiltonian, because you want to have eigenvalues real. So all these things hold in general for require H to be H plus. But the thing is that to have symmetry with respect to, say, for example, PT, that is the parity and time reversal transformation. To have its symmetry with respect to this does not, from this fact, you cannot deduce that the Hamiltonian has to be Hermitian. So people are now looking at non-Hermitian Hamiltonians. So this is what we'll come to in optics. So non-Hamiltonian, non-Hermitian Hamiltonians, Hamiltonians which are used at the moment theoretically, plus there are certain experimental evidence, experimental realization also. One of the examples I go through quickly is PT and PT symmetry. Operator P cap linear, the property is a linear and unitary operator. The action is it changes the coordinate r to minus r, and the symmetry means that the Hamiltonian as a function of p, r and t is the same as the Hamiltonian with minus p, minus r and t. T cap is antilinear and anti-unitary operator. It changes the sign of time. T becomes minus t, and the symmetry remains, which I have written in the last column on the right hand side. Now, combined PT transformation, it is antilinear and anti-unitary, and it changes the sign of r and time as well. In quantum mechanics, the symmetry is achieved if the potential is changed. It is the potential is a complex potential, and it is changed as V star, that is complex conjugation, minus R. If you do that, if the potential has this property, you have PT invariance in quantum mechanics. In optics, I will show you in a minute that the symmetry is realized if the real part of the refractive index satisfies that NR of R omega is equal to NR of minus R omega. And imaginary part Ni of R omega is equal to minus Ni of minus R and omega. If you look at the transformation law, you can deduce yourself that the Hamiltonian, the commutator of the Hamiltonian with PT is equal to 0. Under these conditions, although the energy is not necessarily conserved during the time evolution, the system has a real energy spectrum, given that we have balanced gain and loss. So this is, you see, real part and imaginary part of the refractive index. On average, conservation of energy is achieved. Next. So such Hamiltonian is physical realms. But in I will finish in a couple of minutes. But in electromagnetics, they have become the subject of extensive research since the seminal work of Christopher Dolites and his company. The references I have written here. Today, PT symmetric systems hold a great promise for sensing, imaging, lasing, cloaking, and transformation optics, new mechanism of wave transport topology, light scattering engineering, wireless power transfer, and imaging. The basic concept is paraxial approximation. Write the wave equation as I have written here at the end of the slide, where Nx is the refractive index, is a complex Nr plus INI. Then the above equation, the wave equation, can be written down as a Schrodinger equation with the Hamiltonian, which I have written over here, and in place of potential, I have the refractive index. And then, if you require the symmetry, you will come to the condition I have written down. In general, it is not only valid for paraxial approximation, but in general for the optical system. And the symmetry requires the requirement on the permittivity, which I have written at the end of this slide. Really, real part of refractive permittivity and imaginary part of the permittivity. So such systems have been realized, and lasers, in fact, lasing, the control of laser and things like that. The literature is full of this, and you can look into the literature if somebody is interested. The CP symmetry, that is charge conjugation and parity, such systems have also been are being investigated in optics recently. So these are the symmetry. In fact, there are attempts now to have in metamaterials and other things to have supersymmetric coming into optical systems. So what I mean to say is that symmetry, it is the beauty of physics, and it is there now abundance in optics. People are now using it. So what is beauty? Description and prediction of new phenomena in nature on the basis of symmetry principle is the beauty of physics. When do we recognize the beauty in a physical concept or theory? The answer is, it is when we have understood it. But then where is the difficulty? In fact, the difficulty is in mathematics. That is the language of physics. But then one can always learn mathematics. And therefore, beauty and difficulty are not synonymous in physics. They do not commute in physics. But what about real life? Although the cells in our brain are also governed by the same physical laws, biology leads to some sort of symmetry breaking. In real life, beauties are difficult to handle, and therefore beauties and difficulties are synonymous in real life. Thanks and cheers.
Thank you, Ajit. Thank you very much. Any questions, comments?
Normally, we say that all the big people say that the internal beauty is more important than external beauty. From that point of view, you have equated symmetry and beauty. So the external symmetry and internal symmetry, there is a hierarchy in that? Sir, Ajit sir.
Surani. चलो बाद में बात कर लेना.
I had heard in a documentary long time back that the symmetrical faces look more beautiful. So
Yeah, there is.
I also. Yeah.
Okay, I think let's move on.
There is just one comment.
Yeah.
There is a book called Lost in Mathematics by Sabine Hossenfelder, and the title says How Beauty Leads Physics Astray.
How?
Beauty leads physics astray.
Okay.
Sometimes beauty can be misleading.
Yeah. Okay. All right.
Thank you.
So thank you. Now next talk is by Senthil Kumar, Professor Senthil Kumar.
Yeah, I'm here.
Ajit, you have to unshare.
What? I did not because there was some.
नहीं unshare your slide.
वही वो arrow वाला बटन दोबारा दबा दो.
एक मिनट अनशेयर. हाँ ये एरो वाला तो एक्टिव ही नहीं है भाई.
ये तो कहीं लिखा होगा स्टॉप शेयरिंग.
अनशेयर लिखा हुआ सर. सही भी.
ये अनशेयर लिखा होगा.
नहीं ये तो पूरा आ रहा है.
You move your mouse across the screen, then it will appear.
Okay, let me disconnect and then connect.
हाँ, that also can be done. Yeah.
Okay.
And disconnect करोगे तो वो खत्म हो जाएगा. अभी तो हुआ ही नहीं इसका.
सेंथिल तुम शेयर करने की कोशिश करो.
नहीं होगा नहीं ना. अब होगा.
Okay.
Sir, you can see my screen now.
Yeah. You can share the presentation.
Yeah, are you seeing
Senthil
it?
Kumaran is a colleague in the department. He has interacted with Professor Kehar Singh many
You can
times.
see my screen now.
Yeah.
Yeah. So can you see my screen and can you hear me clearly?
Yes.
Yeah. Please go ahead.
Okay. Good afternoon to everyone. My topic is the Q plate, and I wish Professor Kehar Singh a happy birthday. And this is one of the old photos I could pick up from my old files. On the one side, Joby Joseph, and the other side, I am sitting. And it's a nice photo. I wanted to share it this occasion. Going back to the subject on Q plate, the outline of the talk is that first I will talk about what is a Q plate, then how it is useful in spin to orbital angular momentum conversion. You can convert a spin angular momentum into orbital angular momentum by the use of a Q plate, that I will explain. Then the action of the Q plate in some of the lights, linearly polarized or circularly polarized light, we will discuss. Then how a phase element to polarization element, how this Q plate acts as a phase element. What is a Q plate? Q plate is a spatially varying. Sorry, 1 second. Yeah, Q plate is a spatially varying half-wave plate, basically. So in 2008, Machaviarani has proposed this idea. He has taken a Q plate and cut it into 8 segments like this, and then the arrow marks which are shown in the Q plate are actually the fast axis or the crystal optic axis of the half-wave plate. He has arranged a half-wave plate in such a way, 8 segments like this, and then cemented them together. And in this Q plate, as you see that the optic axis is spatially varying. In fact, he wanted to have a continuous variation, but the technology was not there at that time. So he has come up with this 8-segment type of Q plate he has fabricated in the laboratory. And its action also you will see in the further slides. So basically he wanted to have a, in the figure A, you can see that the fast axis of the Q plate he wanted to have like this. The lines are exactly half-wave plate orientation. He wanted to have all across the cross section of the plate, continuously the fast axis be orienting like this. But it is possible now with the nanostructured materials. This is one way. Figure A shows one type of arrangement of fast axis. Figure B shows the another type of arrangement of fast axis orientations, and the figure C is also another type. And in that figure, these are actually called Q plates, and they are also given different charges. The charges, as you can see, the normal way it is defined, and as you go in the anti-clockwise direction on a circle with respect to the center, and you see the fast axis, they are rotating like this. You start with this orientation of the fast axis. Then as you go in a anti-clockwise circle, the fast axis is rotating in this way. When you complete, by the time you come to the end, it is oriented in the opposite direction. So in a full rotation, the orientation has undergone a change of pi. So it is half times 2 pi. That is why the charge is called Q plate with charge is half. And in the second one, if you put the same way, if you go around a circular path, the orientation of the fast axis will undergo a rotation of 2 pi. That is why we call it a Q plate with charge 1. The third one is also another variant of this. In there also the Q plate has a charge 1 because the fast axis undergoes a rotation by 2 pi if you go across the full circle. And it is also possible to realize these types of Q plates with liquid crystals, and which is can be electronically tuned, and it is now what is shown in this picture is it is shown seen with in a linear polariscope. By using a polarizer, you can see that it is basically half-wave plate is a transparent one, right? It's a spatially varying half-wave plate. By putting a polarizer, you can see fringes like this, which are radially emanating from the center. The center point is the one where the orientation of the fast axis is undefined, so it is a singular point, basically. Electronically also nowadays it is possible to realize that. And another one is one can use meta structures to fabricate such elements. And now we will see a few of the actions where Q plate is illuminated by a plane polarized light, and when it is illuminated by circularly polarized light, what happens we'll explain in this talk. But I will not talk about the third one. When we are illuminating the Q plate with polarization singularities, what happens? That is, the time is short, so I cannot cover the third one. So first two I will cover. There is a lot of things to understand there itself. And let us take a half-wave plate, the Q plate, which is all the black areas show the orientation of the optic axis. And let us illuminate this Q plate with a vertically polarized, that is plane polarized, linearly polarized light. At each location, say for example, you can follow my mouse. So this is the orientation of the half-wave axis of the half-wave plate. This is the polarization direction, plane of polarization. So you will know that half-wave plate only flip it by the other side. Likewise, at each location, the angle between the planar polarization of light and the orientation of the fast axis is differing at each location. Here, if you see, there is no variation. So the same light will come out. Whereas here, there is a 90-degree orientation. So accordingly, it will get flipped with respect to this. And at other places also it will happen. That is what I will show in the next simulation. So the red one shows that the blue color is show the input light, plane polarized light. The output light is having a polarization which is spatially varying. And as you can see that they are oriented like this when the light passes through that. The same thing I will draw it separately like here. So this type of orientation you will get when you eliminate the Q plate. This Q plate has a charge half here, as you have seen in the last slide. And when your Q plate have a charge half, and if you eliminate with a vertically polarized light, you get radially polarized light. Light is vibrating in this direction. All are linearly polarized, but at each location, the orientation, that is, the azimuth is differing. And let us see what happens if you eliminate with the horizontally polarized light. Carrying out the similar exercise, you will see that at each location, the resultant polarization, one can map by going through any point. Let us take this point, and then we can see that this is the light, this is horizontal line, and this is the axis, so it gets flipped on the other side, right? So this way, the light, the blue color incident light will become the output light polarization I have drawn with the red color. And that one, if you draw it separately, it will become like this. So the Q plate, when you are illuminated with vertically polarized light, you get a radially polarized light. And when you are illuminating with a horizontally polarized light, you get a azimuthally polarized light. This is one of the very interesting things. And this is a very revolutionary idea. By spatially varying half-wave plate with a spatially varying property, one can realize a lot of things. And these types of lights are now very much studied because there is a lot of interest. They carry orbital angular momentum, and they are also useful in many other applications. There is a lot of interest in these lights. That also we will see in the coming slides. Okay, there is also another type called the optical vortices, where the wavefronts are having a helical structure like this, which you might have heard in earlier. I was working in phase singularities. These are some of the examples of phase singularities, in which the wavefronts have a helical structure, and unlike plane wavefront, if you take a plane wavefront, one wavefront to another wavefront, there is a lambda distance gap is there. But here all the wavefronts are connected, and it is a single wavefront spanning over the entire space. There are a lot of very interesting properties in, for the optical phase singularities that we are not going to see now. This just I want to introduce the singularities. Sorry, I will. It got closed. Let me open it again. Okay, we are in this slide. Yes. Okay, here in this slide, what I am showing is you have a right circularly polarized light. You can follow my mouse. Right circularly polarized light and left circularly polarized light. Both of them are having a phase distribution which is corresponding to a vertex of opposite charge. If you combine these two, the resultant polarization will be oscillating like this, which is actually azimuthally polarized light. Don't follow these things. These are Stokes phases and other things. We don't need that now. Likewise, if you have the first case and second case, if you see, they look, the charges also have been inverted here. When you combine these two, right circularly polarized light with the opposite charge vertices, you can interchange the charges, you get a resultant polarization pattern like this. Likewise, for the other one, you will get a radially polarized like that, and the last example is like this. So basically, when you have, earlier I have shown the radial and azimuthal polarization, they are basically made up of two helical wavefronts with opposite charges, and also they are made up of both the vertices are in opposite polarization state. In other words, they are having a spin angular momentum are plus half h cross and minus h cross as far as the polarization is concerned, as well as the orbital angular momentum. If you consider, they are having opposite. If the charge here is 1 means this is minus 1. So they are in orthogonal SAM as well as orthogonal Ohm states. They are the combinations. So radial, azimuthal and other things, all of them are combinations of SAM and Ohm states. That is why there is a lot of interest in this type of fields. We can also have higher charges also. We call them basically as V points. There are some V points shown here, and their polarization variations are also shown in these slides. Here I have taken the same RCP LCP combination with the +2 -2 charge combinations I have taken, or -2 +2 charge combinations I have taken. You can also have higher charges also. In each case, you have something called an index, which is called a Poincare-Hopf index, by which you can characterize these beams. How many times the major axis of the ellipse undergoes when you go around one full rotation in the spatially varying polarization. That is a parameter we normally use. And there is one revolutionary paper in which it is shown that when you are eliminating a Q plate, which is having a charge, appropriate charge here, when you are eliminating with a left circularly polarized light, what is coming out is a right circularly polarized light, because obviously it is a half-wave combination. So handedness will undergo a change. Left will become right. But at the same time, this is a plane wavefront falling on this that will turn out to be a helical wavefront on the other side, which is actually shown as, in that paper, it is shown as he has actually converted a spin orbital angular momentum into a pure OAM, orbital angular momentum. So spin to orbit conversion is possible by using this type of Q plate. So it was very interesting paper which appeared recently. And likewise, by changing the handedness of the input SAM state, also one can have oppositely charged OAM state can be generated. So basically, you are having a plane wave here. You have created a wavefront which is having a different shape, which means that wavefront shaping is also possible by controlling the polarization in a local way. So this is also one of the interesting ideas which people can pursue. By controlling polarization, one can realize whatever we need. To understand it further, we will go back to the initial slide once again. We have charge 1, -1, RCP, LCP combination leads to this. Charge 1, -1, same combination here you can see, but there is a phase difference of 180 given between this and this. So this combination gives this, whereas this combination with a 180 phase shift, which means that this can be replaced by minus sign, that will give this. That is what I have written. When you are eliminating a Q plate with the X polarized light, you will end up having radially polarized. +1 charge RCP plus -1 charge LCP gives radial. This in my language I have written. And if you are eliminating by Y polarized light, you will get +1 charge RCP minus, because the 180 shift I have brought it here, -1 LCP azimuth you will get. And when you are eliminating, yeah, I will finish in 2 minutes, sir. When you eliminate with the left circularly polarized light, which contains both X and Y polarization with a 90-degree phase shift, then you will have, you can add these two. Basically, X also is there, Y also is there. If you add, these two get added, this gets subtracted, so you get 2 times RCP. That is what you have seen in the earlier slide. So this way one can understand the action of a Q plate on a circularly polarized light also. And the phase can also be imprinted on the polarization. Some few examples are given from my book. So if you have 2 regions where 0 phase and pi phase, and both of them are linearly polarized, that can be shown by showing this arrow up, this arrow down, which indicates that the phase information is given by the arrow mark. By putting a double arrow, you are not giving any information about the phase. Likewise, 0 and pi/4, it is difficult to show in this, but here I have taken a circularly polarized light where the arrow marks, I have moved it little bit to show pi/4. 0 and pi/2 I can show like this, and 0 and pi, same handed light, but it is shifted, the arrow mark I have put like this, which indicates that the phase information is coded into the polarization. That is why you can do phase engineering by polarization engineering also. You also know that by adding 2 circularly polarized light, you can get linear. By giving a phase difference to that, you can orient the linear polarization to a different direction also, which is also another example where how the phase difference can be brought into a polarization variation. And we have also seen in the earlier example, using a Q plate, LCP converts it to a vertex of charge 2. In that, if you see the incident light and output light, now this device is actually called as a coupler. A circularly polarized light passing through a QA plate with the charge Q will produce a vertex beam of charge 2Q we have seen. In that case, you can see SAM content is LCP to RCP change has happened, as you have seen, which means that plus H cross to minus H cross it has changed. Spin orbital angular momentum, which is 2H cross, is the total change. OAM, if you see, initially a plane wave is falling on it, and the beam coming out is going to have a double the charge, so it is 2H cross. So as far as there is no transfer of angular momentum, but what you have got is spin to orbital complete conversion has happened. That is why that paper is a very interesting paper, in PRL it has appeared. And one can also do some arithmetic with Q plates. This is a Q plate. The output light is viewed using a polarizer to different orientations. It gives light like this, and the resultant polarization going through a polarizer also is shown here for different incident light. Vertical light, if you eliminate, you will get this. 45-degree oriented, you will get like this. 90-degree, you will get azimuth. RCP will give you LCP with a vertex in that. All these things are shown. This is a single Q plate. You can increase the charge of the Q plate by sandwiching a half-a plate between a Q plate. You can do a Muller matrix also, and you can see that one can add the charge of Q plate 1 and Q plate 2. So Q plate 1 plus Q plate 2 is the resultant charge of the Q plate, and all these things are also analyzed using analyzer, polarizer rotated in the output beam at different orientations. This type of patterns one can get. So one can do arithmetic also. One can have many Q plates, and you can just put one sandwich between half-a plates and have whatever charge you want, you can have. So with this, I have come to the end of this slide. So I started with this outline. Now I simply change the title to summary. It is the same slide. So what is a cubelet? I explained in this talk. And second one, what I talked about a spin to orbital angular momentum conversion. One of the nice things I have shown, circularly polarized light I have taken for example. And also action of the cubelet on linear polarization X, Y, and other states I have explained. And I also showed that phase element to polarization element conversion, which means that the element is polarization element, as we have seen. Circularly polarized light is falling on that, but the wavefront gets altered. So even though it is a polarization element, that does the phase conversion, not the polarization in the opposite, it is changing. Phase conversion is possible, that we have seen. And finally, very importantly, after the lunch break, I want to tell you that we have noticed that cubelet is not used in the kitchen or in the dining hall, but in the laboratory. That is the main point I want to drive here. For all of you who have gone to sleep. So now with that, I am ending. And any questions, I am willing to answer. Please. Any questions?
Okay, thank you, Senthil. Any question, comments?
Please.
Sir, what does QS stand for? What does QS stand for?
Q is actually the name given by the Machiavelli, the Italian scientist who has given the name Q. I don't know why he has given Q. Maybe charge. Q stands for charge. I think so.
Okay. Professor Kehar Singh.
Yes. Just a comment to acknowledge or to appreciate his work in singular optics.
Yes, sir.
Long time ago, Professor Senthil Kumaran, Rakesh Kumar, and I did some work on singular optics. Since then, I have been following this work, and his work is very highly cited in the literature. His rate of publication is amazing. I even find difficult to keep track of his research papers. I don't know how he gets time to publish so many papers. So congratulations to him.
Thank you very much, sir. In fact, I work all the time, and I also shared that.
I can tell you whenever we call him for a meeting, he says, "I'm sitting with students. I'll come join a little later."
So I used to tell that referees are torturing me. All the time we are busy with the referees. Yeah. Thank you very much for your kind words, sir. Thank you, Joby Joseph and Professor Anurag, for giving me the opportunity. Thank you.
His book also reminds me of him. He gave me he gifted me a copy, and quite often I go through this.
Okay.
Thank you, sir. Thank you.
Okay, so next is Professor Varshney.
Okay.
Varshney ji?
हाँ, yes.
Yeah, please share. Yeah.
हाँ, वो पहले disconnect करेंगे.
Senthil.
Oh, I think I have disconnected.
Varshney ji, you start, then it will automatically push it out, probably. Yeah.
I think I have disconnected, sir.
Yeah. Okay. Yeah.
Hey, stop sharing.
ठीक है, वार्षिक जी आ गया था तुम्हारा।
मेरा आ गया क्या?
आ गया था।
Okay, sorry.
हाँ।
Okay. So first of all, I wish to.
देखो presentation mode होता है कि नहीं पहले?
Presentation mode में ही है?
अच्छा यहाँ नहीं आता, पता नहीं क्यों। चलो anyway ठीक है, आ गया। Okay, fine, go ahead.
हाँ, वो थोड़ा सा time lag हो जाता है। Okay, first of all, I wish Professor Kehar Singh many happy returns of the day and have a long, healthy and active life ahead. And so the title of my talk is Silicon Photonics, and the layout of my talk is following. First of all, I will discuss some of the brief introduction about the silicon photonics technology, and then silicon waveguides, and then some of the devices like polarization splitter, polarization converter, and then trace gas sensor, and finally I will conclude. So silicon photonics, as you know, silicon is the one of the best material for electronics and VLSI design, and we have a well matured and state-of-the-art technology like known as the CMOS. So if we can combine this with the optical photonics, then we can see like the transmittance of the optical properties, which is for the bulk material is shown here, and this picture is clearly showing that we can have a low loss material for the optics over the wide range, and that is in the range of 1.127 micron. So if we combine this silicon and the photonics together and take the advantage of this CMOS technology, then we can very easily combine a technology which can provide a smaller, faster, and cheaper technology. So a architecture of this integrated circuit is shown here. Like it has a large number of the components over a small piece of the silicon. That, for example, like you are having a laser diode here, and then of course electronic modulator, this purple color, and then we have the splitter. So it can split in the two parts. One is can go to the optical fiber, which can be linked with the waveguide through the V groove, and then it is a Y junction you are having. Then you have a optical amplifier, then direct coupler, and then you can, so we can divide the light into two parts. One end can go to the like photo detector, and then second part can go to the optical fiber. So almost all optical component can easily club together, and then you can make a silicon photonics devices. The growth, if a market survey is showing here, like initially, of course, the silicon technology was not very popular, and so the market is very, very small till 2013. And 2014 to 16, we have a significant growth, and this growth is continuously increasing. So, and people are expecting the projected growth is 2022 is the so now we have a and this can be achieved by silicon splitter with photonic devices. So silicon devices having a large value of the difference between the highest and lowest region. For example, we consider that we have a 2.0 and we consider that so we can make but on the other hand, this is providing high confidence. So to overcome the impedance, the components are provided like a potential splitter and devices with the heavy so to overcome it, devices are difficult. Where they can be put and the common is the next of the sensitive light where the higher the jet, then upon low strategy is and you can see in this computer that we can find it is high density. Recently, so in this case, what is happening? The most of the upper is the in this region. Okay, this is the we can So simply the is like this, and then open the we have a so so we take so we can
ये रिकॉर्ड नहीं हो रहा है।
are basically solid state lighting, LEDs, OLEDs, laser based solid state lighting, and one of the topic we are working here. And communication, you already know, basically fiber optic network, visible light communication, which will be the next big thing. Live 5, we call it free space communication, for example, using light. And all display devices are using all these technologies presently. And apart from laser-based manufacturing is coming a big way. So all these photonics basically technologies utilize minimum input energy and work with the highest efficiency and contribute zero pollution. That is why we call it basically green photonics technology. So let me come to today's topic. Basically, sustainable energy generation by solar cells. Basically, that is well known worldwide right now. So all variety of solar cells are there. So what is our interest is basically use of direct sunlight, daylight saving, and sunlight to home. And in that respect, we are also working luminescent solar concentrators and transparent solar cells. Of course, we procure outside. And future going to be a smart window glasses. They will transmit the visible light and convert heat into energy. And look at this solar energy spectrum. So this is the efficiency of the various kind of solar cells. So very small part of solar energy or solar light is used by these solar cells. But if you look at the visible spectrum, which is basically most of the visible light is not unutilized, and also near IR light is unutilized. So we are looking at how, apart from these solar cells, how can we utilize more and more energy, visible light, and bring inside. And in the luminescent solar concentrator fabrication, we are working on how to utilize the near IR light and do a conversion, bring it the visual light, and also some portion of ultraviolet or blue light can be also converted. So this is the these are the two parts of my talk. So you look at this light source, the spectra of different light source in the visible range, and then you can see the sunlight or daylight is the first topmost. Hello, which is basically continuous in the visible range. And apart from, we have been using for centuries, incandescent lamp, fluorescent lamp, halogen lamp. Now is the LED, and morning there was a question that this LED light has a very narrow spectrum. Of course, it's not good for this one. So we feel that the sunlight is the best light for daylight saving. So we looked at the various kind of concentrators, what we see in the market. Basically, two types of concentrators are low cost and easily basically mountable, but one is a parabolic reflector, which becomes very, very costly, and we have to track it. So we concentrated on the Fresnel lens, large Fresnel lens lenses, which are basically both circular and linear form they come, and they are very low cost and very thin, and their diameter can be very, very large. So we started with this, basically this lens. So first thing was to bring sunlight. This paper was published last year itself. So the most important part in this concentration is basically you have a large Fresnel lens on the top. It will focus light, all the entire light, because the transmission spectrum of this it is of course PMMA lens, so it has a large transmission bandwidth. So you will be having a lot of heat. So heat can be diverted through this hot mirror and towards in this direction. Of course, you can do the TEG based electric generation, or of course some of the heat is of course transmitted. So this part is most complicated. Then we solved it. Basically, you can see here below is the fiber optic cable, basically bundle, and this is a metallic section of conical section. Inside we also of course toughened glass conical shape we erected, and then sometime that was but that got burned. But we circulated the water inside, so water inside out and out coming here. And then we basically did two things, bringing the sunlight. So this was on the rooftop. You can see a significant amount of light coupled to this fiber, and just adjacent to the ambient light. And this is the fiber of 20-meter diameter of bundle coming inside the room. So we computed the amount of light coming inside is about equivalent to 20 watt LED lamp. And we measure the spectrum. So spectrum comes quite close to the sunlight on the rooftop. But there is a dip, small dip here. We could notice this dip is because of the plastic fiber. So if you use a flexible plastic fibers, then we can of course bridge this gap. And otherwise, we were successful to bring sunlight right now up to 20 watt lamp, which is about 80 to 90 lumen per watt, and spectrum is fairly close to the sunlight. So this was the first part of our work. And then this was done with all this rotating and mechanical tracking system. So tracking, we want to avoid tracking. So we decided to make a non-mechanical tracking system. So this is how our combination new design, which was also patented. So you can see here, you have again the huge lens, 1 meter diameter, very thin, and then sun from the morning to midday to evening is a tracking like that. So the focus of the Fresnel lens will be going here and there. So we designed this segmented mirror kind of system with a particular angle. And then what we saw is any time is the sunlight is coming, so it will be directed towards in a particular common direction. So first thing we did is because of the huge energy, we could utilize this for heating the water. So we got, compared to the conventional water heating system, about 20 to 30 degree extra at a time. So this is what is the GMAX design of the system. And this is the difference of solar irradiance by this system, and the huge temperature increase in this one. And this now later on we want to utilize this for sunlight, bringing more sunlight in here inside the room. And this is the next step we did. If you look at the solar spectrum, so it has a visible portion, which is the most prominent one, and then you have a near IR. So you look at the silicon-based solar cells response curve is this one, the yellow one, and blue one is basically transparent solar cells. So we wanted to do for cascading basically. So you have a Fresnel lens again, and below is our the non-mechanical tracking system. And then on the top of that, we placed a transparent solar cell. They are basically perovskite-based, thin film-based, CDT-based solar cells. And you can charge the battery by utilizing the visible light and the IR light, and of course some of the visible light is also transmitted. They can be focused on this water heating system. And then we can do both simultaneously water heating as well as the power generation. So this is the spectrum of this is the entire photograph of our system. So you can see the solar thermal is directly exposed to the sunlight, and then also Fresnel lens focusing on that, and then on the top of about 10 centimeter above you have a transparent solar cell, and this is the transmission. So visible light is basically absorbed by the transparent solar cell, which is 1 meter by about 2 meter, 1 meter width and 2 meter long. And then we can use this one for water heating, and we got excellent result. The results are published in the Energy of Sustainable Development. And then next was basically these are the photograph we had took, and or red color filter. We got very good result with the red color filter lens. And then next was that our single lens non-mechanical tracking system was little bit inefficient in the morning and in the late afternoon. So we got a design of this kind of system. So you can mount it 2 large Fresnel lenses followed by the transparent panels here. And then we can generate huge amount of energy as well as huge amount of temperature, so that we can fully utilize this basically the IR spectrum as well as visible spectrum for both solar thermal purpose and heating purpose, and then we can get enough efficient combination. So you can see here this photograph shows that 2 clear-cut focus spots on this here, the one here, other one there. So this will work efficiently in the morning hours, this will work efficiently in the evening hours, and in the midday both will be working. Then both the focus spots will come very close to each other. Then we can have a very huge temperature or huge amount of light. This is the next thing we want to use for sunlight bringing inside the room. So this is of course the photograph again we saw in our rooftop system, and these are all systems are available now in the rooftop. Anybody can would like to see our system for water heating and for us for this is like, say, you can see the midday both the focus are coinciding, and that is what is the system. So this is what we have been doing, and in future, but very short few slides are there. In future, this will be the greenhouse structure. So this is from this journal of renewable and sustainable energy. So right now you could see greenhouses are basically a white color plastic and something like, but these are basically transparent solar cells and luminescent solar concentrators. The red one is the luminescent solar concentrator. This is the transparent solar concentrator, and that kind of transparent window glasses will be in future. So what is the concept? The concept is this. Yes, sir. Another 2 minutes. So this will be basically absorbing the some of the IR light, and then this glass is basically embedded with the phosphors, up conversion and down conversion phosphors. So they on the side some because of the total internal reflection, the light will be concentrated, and you can use this thin film high efficiency solar cells for power generation, and the visible light can be used for room lighting and all those. So this is a future house. So is a luminescent solar concentrator looks like this one. It is basically glass or a polymer sheet embedded with the different color luminophores, and then the light will be basically generated light will be the total internally reflected. In the edges you can see the concentration. You can put the transparent solar cells, and we have been able to develop such kind of phosphors by absorbing basically same phosphor can basically work for converting up conversion, and of course combination by make the down conversion. Both bring the sunlight in the middle portion. These are some of the small luminescent solar concentrators of up conversion. And then this is the yellow phosphor also we use, and this is the transparent. So 1 feet by almost about 8 inch, 8 inch by 8 inch transparent solar luminescent solar concentrator, and that can be used for kind of window glasses, something like that. So this is another one. So all of course up to the first prototype to develop, and would not show you here. And for all this work, we have a big team of Green Photonics. So these 3 or 4 PhD students working with me, and also because it is a huge technical work on the rooftop. So we have got a lot of people working on this, and the project was funded by GST. And thank you very much. So we have published now all these in the particularly in the sunlight harvesting many papers, and also laser-based solid-state lighting many papers we patented. And then this is the recent one of the technology of solar tower array we have basically transferred to this Hitesh Mehta company, EP Sunsol Private Limited, very last month. So they are now very happy building a huge high efficiency solar tower work. And that with that, thank you very much.
Okay, thank you, Professor Mehta. Any questions, comments? Okay, if there are no questions and comments, then let's move on. Unshare kar dijiyega.
Yeah, okay.
Now next is Professor Kehar Khare. Kehar, are you there? Yeah, okay. So
Kehar, you are muted.
Kehar?
Yeah, okay. Can you see my slides?
Yeah, now.
Okay.
Yes.
Yes.
Go ahead.
So today I'm going to talk about, since this is a symposium in information optics and photonics, I'm going to talk about imaging from an information transfer perspective. First of all, I would like to send my wishes to Professor Kehar Singh on this very auspicious occasion, 80th birthday. He has been a big inspiration for me. I have never really worked with him directly, but I have known him for more than 20 years now, almost. First through his work, and then in 2003 during my PhD, I met him. So since then, I have always kept him updated with whenever I do some new work, and he has always been very encouraging for pursuing new ideas. I want to kind of get a overview quickly in 2 slides of how imaging has become very important in today's science and technology, and also in our society. And so if you look at this whole spectrum of sub-nano to astronomical dimensions, I think imaging is playing a very, very important role because, for us, a good way to understand any phenomenon or how an object looks like or how things work is to take a picture of that. Okay. And so if you look at these 3 systems, I have shown here 3 different pictures. The physics used is quite rich. So if you look at it, the virus imaging actually requires electron beam, cryo-electron microscopy. If you think about MRI of a head scan, then you need magnetic fields plus detection of Larmor frequency due to spin flip. And then the last one, which is the Event Horizon Telescope, which is a large array of antennas, which is Earth-sized antennas, meaning located at 6 different locations on Earth's surface. It is actually requires coherence theory because the basis of the data is actually the correlation of signals from antennas, and it is related to the Van Sittard-Zernike theory. So there is a lot of diversity in how imaging is used, and the physics is really varied. Applications are really varied. I would like to still venture into making 2 classes of imaging systems, classify them in 2 different categories. First is a traditional imaging. I have shown these applications which are kind of new, but still, if you look at mobile camera or digital pathology or self-driving car, all these places, the hardware directly provides the image. Okay, so there is nothing new in that. So there is still a lens and a sensor behind it, and the processing is mainly used to make the image look better or make some decisions based on that picture. But the new class of systems, which I call as computational imaging, you can take planoptic camera, super resolution microscopy, MRI, CT, all these examples. Inherently, there is something new and different, is that the hardware actually doesn't provide the picture directly. It provides numbers that cannot be arranged to make a picture, but the algorithms also generate the picture. So algorithms have a very important role to play in all these systems, because the algorithm is not there, then you can't even have a meaningful picture in the first place. If you look at it, these are a very diverse set of systems, but they are kind of connected by one overall, system picture that I have drawn here. So you have a source of light, and that illuminates some object, and these scattered waves from the object actually encode information in various different forms. So this information could be in terms of intensity, phase, polarization, spectrum, coherence, any other forms of correlations. So once you have a imaging system hardware setup, then all this information is actually entering your imaging system hardware through the aperture. Now, traditionally, the most of the work in imaging, at least in optical imaging, involved designing lenses so that the picture that you see on the camera is as perfect an image as you can get. But with this computational imaging as an idea, this requirement is not there. Meaning, you don't have to detect something that is visually meaningful here, as I have already shown a few examples. And what matters is how your hardware and the image reconstruction work together. And most of the times when they work together in an interesting way, you can get unprecedented kind of performance in terms of resolution, noise, multidimensional information, and things like that. And so eventually it allows you to see things better in a different way. So this is a very interesting, this kind of ideas have a lot of future. So the central questions, if you ask me, what are there in the terms of these imaging systems is, these are really mathematical questions, basic questions. And these questions are like, how many measurements are needed to generate an n pixel image? And can the measurement scheme be changed compared to what we are doing right now to do something better than what the conventional systems cannot do? And given this unconventional kind of measurement schemes, how do you actually reconstruct a meaningful image out of that? So all these questions are important. They are kind of basic questions. But what is the implication that if you can answer some of these questions, then it also leads to a new concepts and imaging devices. I'm going to quickly show 2 or 3 examples from my recent work here. There is a lot of work in this space in general. As a new faculty at IIT Delhi, it's almost 10 years ago, I started looking at this problem of how well we can recover phase information from single interference pattern. Now, if you look at this interference pattern, the object wave is actually a step phase kind of object. So you can see that there is a discontinuity in the fringes. But traditionally, the single shot holograms, they are processed this way, that you take a Fourier transform. This shows the magnitude of Fourier transform on a log scale. And so you go to this cross term peak and you filter out some region. And so when you take an inverse transform of this region, you recover this phase. But you see that here, there was a sharp discontinuity in fringes, but we have lost that because this operation is really a low pass filtering operation. And so when we investigated this problem a little more in detail, we came up with a new optimization algorithm that can recover this full resolution as it is in the hologram. And there is a lot of publications we have done in this area, but beyond accuracy, it also showed us that we could, the noise performance of this method was also very interesting, that we could kind of beat the traditional short noise limit for the overall phase map. Now, once you have a new idea like this, that even a traditional data can actually lead to more information via a new algorithm, then it's really a case for building a device. And that is what we did. Made this microscope, which is a single shot full resolution microscope, which is at IIT Delhi CRF central facility now. We have also some prototypes in our lab, but in general, a traditional microscope, if you look at the cells, this is what a pathologist sees today. But with this microscope, if you record the interferometric image as well and apply this algorithm, you can also get a very high resolution phase map of this nucleus. And this has many interesting applications in live cell imaging for biosciences, pathology, diagnostics, things like that. With this instrument now in the CRF, we hope to have a lot more work, in using this instrument. It will be really nice if people in biosciences can independently use this unit and produce some nice publications and see some new science in cell biology. I would like to take to another kind of modality, which is structured illumination, where in the first example I showed you, there was no change made in how data was collected. It was just shown that the data has more information than what traditionally it is thought one can recover. But you can also change the measurement scheme. For example, here is an example of structured illumination, where here I have shown pictorially. You illuminate an object in a microscope. These yellow rays that I'm showing, they enter your system. The orange rays, they go out of the system, so they don't contribute to image formation. So this kind of system, is limited in the resolution by the Rayleigh resolution limit. Okay, but if you do a tilted illumination like this, these large angle scattering rays, they can actually contribute to image formation, and you can get something like this. This is not a very meaningful image, but if you collect many images like this along with this basic image, then via a reconstruction algorithm, which is known as now Fourier ptychography, you can actually recover a high resolution image. This high resolution image actually beats Rayleigh resolution limit of this microscope objective. So if you can collect the data in a different way and process it in a sophisticated algorithm, then there is a hope to beat something like a traditional resolution limit. And these are very common things now, meaning this is not just in simulation, but real systems exist that do this. Here is another system that we have been working on, which is extending depth of field. This is an old idea, but we have some new twist in the processing. But the thing is, if you have ordinary camera, if you can see only one plane in this object will come into focus at a time. And so you have to keep varying the focus. But if you have these image stack, in a computational camera, you can actually bring all these planes into focus. So you can see objects from 15 centimeter all the way to 5 meter are actually all in focus in one plane. And so this is very interesting because in any application like robotics or self-driving car, all decisions are made based on focused images, and if you can get all in focus kind of images, it is really, really interesting. The last example I'm going to show is something really new, which we have done recently. I already talked about structured illumination before, where you are using angled illumination. So you are doing some sort of structuring to the illumination pattern in the object domain. Yeah, but you can also do the structuring in the Fourier space. So, for example, and if you do that, it is called as PSF engineering. And the recent work I'm going to show, this is just accepted, is this. So if you take a 4F system, the standard PSF may look like this, and your detector may have some size. So if you have an object that is big, your detector may not be able to see all of it. So the detector only sees only this part. This is because from the object side to image side, there is a one-to-one correspondence, and so there is no real way to measure what is outside. Unless you are going to move the object or move the camera. But if you can do PSF engineering, you can actually get an engineered PSF, which is now instead of one dot like this, it is going to be multiple dots, and so it is an engineered PSF. You can imagine what kind of phase mask will be required. It will be a combination of many plane waves essentially, and that phase mask will read to this kind of a PSF. Now, if you do this kind of PSF, what happens is, on the truncated detector, you get a data that is completely scrambled, a version of this whole big object. But this, the thing is, because of the delta functions are there, meaning these points are there away from the center, this information from outside is actually getting scrambled into the detector. And so if you use this scrambled image in an algorithm, then you can actually do, meaning this sparse recovery like ideas that we apply, you can actually get a full image like this. So in effect, what we are doing is, by engineering the PSF with an algorithm, you can actually increase effective area of your camera sensor. So, there are many interesting ideas, if you allow for this possibility that what is detected on the sensor is doesn't have to be meaningful to your eye. There is so many things you can do that, you cannot do this purely by optical system design, and you cannot purely do this by algorithms, meaning if you have this image given to you because your detector was only this much, there is no algorithm that can fill this information outside. But if you do this, you can actually hope to fill the information outside and get extended field of view kind of detector. I will try to not elaborate too much, but I will just give two directions that I feel are very important for imaging research.
Yeah,
and these are
yeah,
this is my last slide. Okay. So the first direction is if you change how you measure data, how much data is measured, and introduce these new algorithms, then imaging systems that are beating the conventionally perceived limits can be designed or conceived. And so if you can improve resolution, speed, robustness with respect to noise, multidimensional information, etc., then essentially you are going to observe phenomena on a new scale, and you are going to contribute to doing new kind of science. So this possibility of having these devices means that you can do new science. And the second thing, which is also very important, is that we really have to ask, if you think about high resolution system, are we doing things in a little bit of a brute force way? Which means are the so-called premium systems really premium in terms of their price to performance? And this idea of simpler systems with low-cost hardware and algorithms that match the performance of the more premium systems. This has a lot of implications for enabling access to these technologies in various social settings. And so both these directions are exciting because you can either beat the science, or you can also enable access to technology. And so this ideas, we have been exploring these ideas, various ideas, and meaning this is where I want to stop. And any questions, I'll be happy to.
Okay, thank you, Kedar.
I have one question.
Yeah.
Yes.
You told that you can increase the size of detector. So how much you can increase, and you can increase only within the paraxial domain, right?
Yes, more or less, but you can go almost double the size of detector here. So 4x pixels without losing resolution, actually.
And this response is symmetric, circular symmetric?
It is not symmetric, actually. Symmetric is not good because it can allow solutions which have folding in them. Okay. So you make it slightly asymmetric.
Okay, another question. There's one more.
Yeah. Sorry, you mentioned about the Fourier typography. Yeah. You mentioned about the Fourier typography concept. Yeah. So, to obtain the high resolution image, we need to acquire a large number of low resolution images. So, what should be how much should be the spatial spectrum overlap should be there to get an accurate image?
This is an interesting question because right now the spatial spectrum overlap is mainly for convergence of algorithm. If you could do less measurements, that will be great. But right now the number of measurements are way more than, meaning at least what is in the published literature. I also feel that the number of measurements is much more than the resolution gain. So there is some problems unsolved sitting there actually.
Thank you.
Okay. All right. Thank you, Kedar.
Yes, thank you very much.
Okay. Now next talk is by Gufran. Gufran.
Yes, I am here.
Yeah. Okay, Gufran. Kedar, you can unshare that.
Can you please unshare? Okay. So.
Yeah.
Professor Anurag Sharma, can you please see my slides?
Yeah, it is available.
Okay.
Go ahead.
And it is moving also?
Yes, it is moving, but it is not full screen. I mean, it's not presentation mode, but it's okay.
Okay. Now?
Now it is okay. Yeah. Okay.
Yeah. Okay. So, okay. I think now 50% of the work is done if the slides are there and they are moving. Okay, so I will start by wishing Professor Kehar Singh on his 80th birthday. It is really a landmark to reach this one, but the way he reached, that is very important, that with the dedication and with all the enthusiasm and all the inspiration which he had been for all of us who are sitting here. So that is a special thing with him. So with this, also I would like to thank the organizers for choosing the very accurate date. So exactly the 3rd July. So there is no error, there is no need to measure any accuracy. So it is dot on 3rd July. So for that these organizers need to be congratulated. Let me go ahead with my talk. We in our center are working on freeform optics since I joined in 2011. So this is basically a fabrication task and a metrology task which are involved in development of freeform. So I will basically talk about the challenges related to fabrication and characterization and some of the work which we have done to address those challenges. A little bit of introduction I will give about freeforms, then we'll go to the exact manufacturing and characterization things which we did here. So as introduction to freeform, you see that traditionally we have been using all spherical optics in the system since centuries. And these are basically because of ease of manufacturing and the design, and especially the testing also, because there are standard testing procedures available. But we end up with a spherical aberration and other aberrations if we have only spherical optics in the system. We can of course remove these aberrations, but the number of elements which we would need if we are using only spherical would be very large. So then aspherics came into play to basically remove the spherical aberration from the system to reduce the weight and all, and it was mainly initially used for all the space applications, but then it penetrated into the lithography systems also. It had excellent metrology techniques available with computer generated holograms and null interferometry and all. Later, by adding the diffractive structures into these aspherics, one can even play with the dispersion. So that is a very important thing, and that makes the whole system even more compact, especially the systems where the hyperspectral imaging or something like that is required. But until 2000 or so, it was all spherical. It was all basically rotationally symmetric. Even aspherics were all rotationally symmetric. But if your system is having some higher order errors like non-rotational symmetric errors, you cannot remove them by using aspherics. Any number you add, that you can't do it. So the freeform is the only solution if you want to remove the higher order aberrations in your system. Of course, there are many challenges with the freeform: the design itself, its representation, its manufacturing and testing. The same thing which added on aspheric as a diffractive structure on freeform is the current trend where people are working, and mainly about hyperspectral imaging. So we need to write diffractive structures on freeforms. The freeform definition traditionally is any non-rotational symmetric component can be freeform, but from a fabricator point of view, if you need a third axis in their fabrication system, the fabricator will call it a freeform. A designer will call it a freeform when he has at least two variables to play with. Of course, it offers many more variables, but I'm just talking about the minimum ones. Advantages are many. As I said, that it makes the system very compact. The aberration control becomes very handy. It increases your field of view. It can generate many complex beam shapes together. Because of that, it has a lot of applications. Historically, freeform was used in non-imaging applications, especially because of the loose tolerances which we need in non-imaging systems. But nowadays, it is slowly moving towards imaging applications also. So now freeform is not just an area. So I would say that whosoever is working in optical design, designing the system and all, freeform is he has to encounter. So it's not like just we have some area which is called freeform. So the applications are from very small size to all large size, very low cost to high cost applications like in the telescopic systems, head-up displays, even lithographic systems. So it is now applied everywhere. this is the whole range of applications which you can see. The recent ones are imaging spectrographs, where the grading on a diffractive structure, which we call diffractive freeform, can be used. So the question is freeform a new concept? Of course, the answer is no. People knew it long back, especially in the ophthalmic industries. You can see that in 1959 there were work on multifocal ophthalmic lenses, and one of the most innovative work which was done by Alvarez by having a cubic faceplate type of structure for playing with the focus. This today it will be called as a freeform, but at that time he didn't call it a freeform. There was another work by Plummer in 1982, and he also used the word unusual optics. So at that time nobody used the name like freeform, but people used to call it some unusual optics or variable power optics or something like that. As I said, that the fabrication and metrology were all the major impediment for its use in the system. With the new fabrication technologies available, new metrology tools available, high computation is available now. Coupling all these things, now it has become possible to make freeforms. But of course, there are many challenges. Whenever there are a lot of freedoms, there are always a lot of challenges to optimize all those parameters. So fabricators are also facing a lot of issues when there are many parameters to optimize. Ideally, we would need a high resolution in situ measurement on the machine so that we can meet the demanding tolerances. From the fabrication, from the metrology point of view, we would need to know that any error which is coming is that why it is so, and what are the techniques which we can measure. So we have to isolate all these errors into different frequency regimes and measure and find out the reason for their appearance by using our measuring tools and the parameters which we have. So isolation of all these errors and relating it to the particular reasons and then working on it is the real challenge for metrologists. So what we did here in last years, I think I will just take 3-4 minutes and we'll finish it very quickly. Our major areas were in all metrology and fabrication. We did some work on the design also. So initially we started using mechanical profilers and optical profilers to test it, because you see that it is a very heavy technology dependent activity. So whatever and wherever we could get the access to the technology, we used it, whether in India or through our collaborations in Germany. We used all those facilities, whosoever had it. We developed a computer generated holographic a switchable Magenta interferometer which could measure the freeform in a interferometric setup as well as in a slope based measurement system. Then we realized that of course having a computer generated hologram is still a sort of golden technique now, and it gives you very accurate and precise results. But the problem is that all the time you cannot afford to have a computer generated hologram for every individual design of the component. So we started thinking about that, can we have a slope based measurement technique which would be much cheaper and which will offer some flexibility to put it onto the machine, because interferometric setup with computer generated holograms etc. is very hard to put it on the machine. So we started working on a Shack-Hartman sensor based slope measurement technique. We developed our sub-aperture scanning scheme for measuring different sub-apertures on the freeform and then stitched together. We developed it for the transmission mode. For any fabrication error, when the machine is fabricating, so you need to know exactly the error on the surface, not on the component as a whole. So you need to develop the technique for reflection mode. So that also we worked on. Then there were a lot of error estimation analysis had to do, a lot of reconstruction and registration errors come along when you take multiple measurement and stitch them together. So we kept on working. So all the idea was that somehow we should be able to measure towards an absolute way. There should not be any systematic error. Of course, so far it has not been done for freeform anywhere in the world in an absolute way, but we are trying to reduce all the systematic errors which are coming because of any systematic behavior. The idea was that whatever methodology we are developing should be used to make a better component while we are fabricating it. So we had a student from CSIO Chandigarh. There we have a diamond turning machine. So we had a slow tool servo configuration. That means a third axis into the 2-axis standard lathe machine. So we did a lot of process optimizations and error compensation mechanism we established to develop a better and accurate freeforms. So you can see that there were at every step there was some improvement. There is no time to go through each and every step. We developed the alignment strategies also, because for the freeform, whenever you are placing it on the machine, once you fabricate it, and if your metrology tool is not in situ, then you have to take out the component, measure it, and then put it back. And alignment is an issue if you are not at the exact position, so you will never be able to compensate the errors which were there in the previous cycle. There were work done on polishing side also, so we developed some flexible polishing pedal techniques on the machine. The in situ measurement which we developed, we verified it for corrective manufacturing. Currently, we are working on the fabrication of de facto freeforms. Our first initial results have come, so we are still progressing on it. We have worked on the design also, design of a laser spot illuminator for laser projection systems. Here we use structured surfaces. Sometimes it is called structured freeforms. So for the projection and uniform LED illumination, we work on it. In conclusion, I can just summarize it by these two pictures. That the first one on the left you see is what was the status when we started in 2012. We did this fabrication through our collaboration in Germany. So the peak to valley which we could achieve was 7.7 micron. But now with all the work, with all whatever publications come in and all, including all those work on metrology and fabrication processes and all, we could now reach to peak to valley of 0.18 micron. It is quite close to lambda by 4, which we have to use it in an imaging system. So in future, we want to bring it down to the accuracy of the state of the art, like lambda by 10 helium neon laser. So that is a challenge, and we are working on putting our metrology tool onto the machine for in situ measurement and all. With all this work which we have done, now we think that we are able to develop all the critical optics like freeform, aspherics, and diffractive for the strategic space and defense applications, because this is right now the demand from defense, and we have already running one project dedicated to freeform. There are others on diffractive optics. No. One thing I would like to tell here that as a community, somewhere we are lacking to have a design expertise. So we should do a lot of work on optical design, because the freeform needs a lot of design activities. If you design, if you put your innovation into the design, then all these things what fabrication and metrology can bring, so that we can realize the real design and the real system. So with this, I will stop here. I thank the organizers and best wishes to Professor Kehar Singh once again.
Thank you, Frank.
Any questions?
Any questions? Any comments?
Yeah, Gufran?
Yeah, Poonam.
Yes, sir.
Sorry.
How about,
yeah.
How about double freeform systems?
Yeah.
Double freeform form.
Yeah, I can understand. Double freeforms are, sir, right now, so far, people have not made it because of lot of problems on the alignment issues. If you make it
designs.
Some of the designs, yes, but not many. Yes, for space applications, yes, there are some designs, but on one side they are always having very shallow design, on the other side they have some real design. So splitting the power into two is always a good thing. So that people are doing.
Okay, thank you.
Yeah, hello. I have a question. Like you mentioned some of the systematic effects that can play a role. So what are those systematic effects that you expect, and what is the order of error that they can bring in?
Okay, so if we take an example of interferometric setup, then you have always your collimators, and even if you are using computer generated hologram itself will have some errors in the flatness of that fused silica on which you are going to write. That is also a problem. The writing errors are also a problem. So even you have to characterize your computer generated hologram.
Yeah, but what is the how do you measure them, or how do you estimate them, or how do you take into account?
Yeah, there are many techniques. One of the technique on which I myself worked long back during my PhD time was a standard 3-position test, which is done for spherical one. We extended that for aspherics. So there we wrote a dual computer generated hologram. There were two wavefronts encoded on the same computer generated hologram or the same element. And you can characterize or measure all the systematic error by using a spherical wavefront which you wrote on the computer generated hologram, and the other wavefront can be used to measure the component. So it itself is a huge field to make a measurements absolute.
Okay, thank you.
Okay, may I ask one question?
Yeah, who I could not read.
Yeah, I am Pradeep here.
Okay, please.
Yeah.
Please.
What is the substrate material you have used, and what kind of roughness values you have got?
Okay. So far we have used PMMA, aluminium, and Stavax. Stavax with the purpose for making a mold. But most of the work was on aluminium and PMMA. The surface roughness is of the range of around 20 nanometers. Surface roughness is an issue when you are using a slow tool servo configuration of diamond turning. So that is a issue, and for surface roughness, that's why we are working on developing in situ polishing techniques. By putting a sub-aperture polishing technique, you can improve the surface roughness.
Okay.
Okay, thank you.
I think we can close here, and thank you. This session is now coming to an end. Joby, you can
Yes,
take
sir.
over, and we are about 40 minutes late, so we have to push it.
Let's see. Thank you, sir.
Yeah.
So welcome all, and we are in the last session, and this session contains talks by two of his Professor Kehar Singh's current colleagues, where he has set up a new research team, and both of them are currently here to give their presentation. And the first one is by Dr. A.K. Yadav, and after which we will have Dr. Phul Singh. So Dr. Yadav, are you ready?
Yes, I'm ready. I just wanted to confirm whether my screen is
it's
shared.
available. Yes, correct. It's fine. Thank you. Go ahead.
Okay. Is it already in slideshow mode, or do I need to put it on slideshow mode?
Currently, it is not in slideshow mode. Can you just go to next slide? Let's see whether it works.
Okay.
Yeah. It's fine. I think you can go ahead.
Okay, it's fine. So good afternoon, everyone. At the outset, I wish to thank the organizers for giving me this opportunity to be a part of this seminar on information optics and photonics. Congratulations to the organizers, Professor Anurag Sharma, Professor Joby Joseph, Professor Renu John, and Professor Naveen Nischal for their very kind and thoughtful gesture of celebrating 80th birthday of Professor Kehar Singh, one of the most illustrious professors of IIT Delhi. I knew Professor Kehar Singh from the IIT days when I was doing MSc in mathematics, and later on PhD in atmospheric science in air quality modeling. but I came in contact with him for professional interaction when I was at the North Cap University, erstwhile ITM University. So that was in 2012-13. So it has been a wonderful journey of nearly 10 years of working with Professor Kehar Singh. He has been a mentor and an inspirational guide who introduced me to this interesting field of optical image processing. Sir, on this auspicious day of your 80th birthday, I wish to extend my warmest regards and offer my heartiest greetings. As was mentioned in the morning by one of the speakers, it's true that with the extraordinary energy and enthusiasm, you are just 18 years old with 62 years of experience. We at the North Cap University used to wonder how come you have such high energy levels even after working for the whole day. And I have never seen you tired or fatigued throughout. So you truly inspired several generations of researchers and are continuing to do so. My sincere gratitude to you, sir, on this special day.
Thank you.
I'm going to restrict my presentation to a kind of overview of the personal journey with Professor Kehar Singh for our professional interaction. And it has involved several collaborators, Dr. Phool Singh, Dr. Sunanda Vashish, Dr. Hukam Singh, Dr. Ravi, and some students, PhD and master students. And then there are 3 organizations who have collaborated for the work. And together we have published about 20 papers in some of these leading journals, optics and lasers and engineering, applied optics, optics communication, and so on. While exploring the field, we looked at various systems like symmetric crypto systems, asymmetric crypto systems, as has been talked in the earlier presentations, linear and non-linear, taking into account the use of random phase masks or structured phase masks, and then taking up studies on image encryption and watermarking, considering schemes for grayscale or binary images versus color images, and then use of full transforms versus their fractionalized versions of mathematical transforms. And we also looked at use of several chaos theory based crypto systems, and in the process we did some crypt analysis also, looking at some attacks. So, I don't wish to repeat, but we all got started with the classic Bridger and Javidi in 1995, which has more than 2,600 citations now. And one cannot overemphasize the need for information security in this era of internet and social media. This is a very conceptually appealing, a simple scheme of DRP, double random phase encoding, with a simple mathematical expression for encryption and decryption. And optically, it is corresponding to this 4F system, wherein we looked at applying various full transforms like Fresnel, Hartley, gyrator, and we also looked at fractional Fourier, fractional Malin, fractional Hartley in various crypto systems. Also, it has been mentioned that the classical schemes were found to be vulnerable to various attacks like non-plain text attack or chosen plain text attack. In Peng in 2006, Peng et al. Exposed this vulnerability, and it led to development of asymmetric crypto systems. The first attempt was made by Qin and Pang in 2010. Soon thereafter, in 2012, this was also shown to be vulnerable by Wang and Zhao in 2012. And then we also looked at modifying this, phase truncated Fourier transform to develop more resistant crypto systems for grayscale and color images. So in our attempt, we also ventured out to look at the use of fractional Hartley transform. The fractional Hartley, the Hartley transform expression is for a function of single variable is given by this infinite integral, and the Hartley kernel is given by cos plus sine. It leads to a real value transform. And the interesting property of the Hartley transform is that it is its own inverse. Then the fractionalized version of this Hartley transform for a function of single variable fx is written like this, in which the kernel is more complex now, and the full Hartley transform was real valued, whereas the fractional Hartley transform actually is a complex value. If you look at the two-dimensional version of fractional Hartley for a function fxy, which is given again by this expression, and where you could see on the right hand side there's a double integral, and the parameters like wavelength, focal length of the lenses, and you could see that this is a fractional Hartley of fractional orders p and q, which are also coming in the expressions for phi1 and phi2. So we've used this fractional Hartley transform to explore several cryptosystems in the category of symmetric as well as asymmetric cryptosystems. So I'll first, and then when it comes to optical implementation, it is quite convenient if we express this fractional Hartley in terms of fractional Fourier transform through 4-channel way. And 2 channels are represented by the direct fractional Fourier transform, and 2 are using the inverse part. We looked at how it manipulates the input image. This is a grayscale image, and its fractional Hartley transform is given in the middle, and the corresponding histograms are shown in the second row, and we could easily see that how the fractional Hartley transform transforms the input images. So this is the beginning of the journey, and we started with the symmetric cryptosystems, wherein the encryption keys and the decryption keys are the same. And the first study that we looked at was for phase image encryption using Arnold transform and singular value decomposition. So you could see at the top the encryption part, and then followed by the decryption part. And this work was published in Optics and Lasers and Engineering in 2017. Then we developed a color image encryption scheme using affine transform, where the color image was decomposed into RGB components, and then we applied fractional Hartley. Before that, we used random phase mask, and then we used affine transform on each of the components. And finally, again, second fractional Hartley, and we got the component-wise encryption.
Can you please finish in 1 minute?
And this work was published in Optica Applicata. Then we used, structured phase mask in one of our studies based on Devil's Vortex Fresnel lens, and the scheme is given here, which uses the Arnold transform along with the fractional Hartley transform. And this work was published in Journal of Optics. Then we also looked at the asymmetric encryption schemes, and this is a scheme for color images, and you could see it uses affine transform along with the fractional Hartley transform. And this work was published in Journal of Modern Optics in 2019. We also looked at use of fractional Hartley in watermarking using a modified equal modulus decomposition. You could see the scheme encryption at the top, and then just below it, it gives you the image form of the scheme. And then at the bottom, you see the decryption scheme. And this work was published in Journal of Optoelectronics and Advanced Materials. I'll just show you 2 more slides. This is with the noise attack. We've carried out various attacks, but then due to paucity of time, I'm showing only the noise attack in one of the schemes. And you could see that it was fairly strong enough to resist the noise attack. Also, the occlusion attack results that we got in one of the schemes, which was published in Journal of Optics. And we also published a work which was based on cryptanalysis, that is non-plain text attack using particle swarm optimization algorithm. This work was published as a book chapter. And we also published a review article on the schemes based on fractional Hartley in Asian Journal of Physics. We recently published another work which was mentioned in the morning by Professor Kehar Singh using nonlinear mask. So our journey to excellence continues, and once again I thank the organizers and Professor Kehar Singh for giving me this opportunity and introducing me to this interesting field of image processing. Thank you so much.
Okay, thank you, Dr. Yadav. And in case just one question, it's
sorry.
Okay, thank you, Dr. Yadav. Then we will go to the next speaker, Dr. Phul Singh, who is the second contributor from Professor Kehar Singh's current group.
I'll have to stop sharing.
Yes, just press that share button once again.
I have stopped sharing.
Dr. Phul Singh, can you share the screen?
Yeah, I have shared the screen. I hope
we don't see that. We don't see your share.
Now it is visible, sir?
No.
No. Now it is, sir?
No.
Okay. Now it is, sir?
Yeah. It's Now we can see the screen, computer screen. You can load your presentation. All right.
Can you see my presentations, PPT, sir?
Yes, it is coming.
Okay. Good evening to all. On the outset, I would like to thank the organizer to give me this opportunity on the occasion of 80th birthday of my mentor, Professor Kehar Singh. So, happy birthday, sir. My presentation evolves around the chaotic map and their application in optical crypto system. This is basically just the extended presentation of Professor A.K. Yadav, the previous one. Chaos, or we say, which is exponential sensitive to very small perturbations, appear everywhere in the nature. A system is chaotic if it is bounded. Bounded means that, like a planet circling a star in its dynamic state within an orbit, rather than escaping off to the infinity. And it is deterministic. Deterministic means that the exact initial condition will produce the exact results. And if any tiny perturbation to the system get exponentially amplified. The great meteorologist Edward Lorenz famously described the chaotic phenomena as a butterfly effect. In a chaotic system, something as small as the flapping of a butterfly wing can cause as large effect as a tornado. For example, weather reporter might take a nearly identical forecast for two different areas, meaning that they have the same initial conditions of the system, but within a week or 2 weeks, the weather pattern are completely different. So therefore, this erratic or random behavior of chaotic system, which are deterministic in nature, need to be studied. To study them, we require to know mathematical concept, how it iterates, what is fixed point, their stability, Lenovo exponent, etc. By iterates, I mean if a function, defined at a point fx naught, then we again apply that function on that, and again we are getting a loop basically. In general, if you just write xn plus 1 equal to a function of action. For example, if we have a function as cos x and we give initial condition as fx naught, then first value will get 0.5, then this, and it keep going, and we'll get many values, but we are not getting the periodicity in that. Similarly, a fixed point is defined as a point where functions has the value.
Sir, your screen is not visible.
Is it visible now?
Yeah, it has gone. Now we don't see that it has gone out.
No, sir. I guess you have stopped presenting.
You might have pressed a button unknowingly.
Okay, sir. Wait. Yeah. Now it is, sir?
No. Maybe you press the share button again and come back. And share and come back. Share.
Okay. Let's open share. Desktop. This way. Now it is, sir?
No. Yeah, it is coming. Yeah. Okay. It is there in the IoT.
Okay. The fixed point basically fx equal to c. Graphically, we just draw a line y equal to fx and we see where the point cut. It could be stable or unstable depending upon the condition. If function's derivative at that point is less than 1, then it is stable, otherwise it is unstable. For example, if a function, say x square, it has 2 points at 0 and 1, where y equal to x cut the curve. One is stable at 0 and another is unstable. To know the chaoticity, let's chaotic system. I'm giving a very simple example of 4x minus 4x square. I'm taking 10 to 12 points, and after 100 points, you can see that there is no periodicity. You can't predict what will be the next point where it will go. For example, chaotic behavior can be seen from the bifurcation plots also. Lyapunov exponent is a very mathematical method to find whether a function is chaotic or not. If Lyapunov exponent is positive, then the system is chaotic, otherwise system is non-chaotic. To show you how we calculate Lyapunov exponents, suppose we consider a tank map, which is given by this expression, and its derivative is quite simple. We can calculate, and if we calculate its Lyapunov exponent, it is log r basically. If we plot after 1, we'll get positive values, and this is the bifurcation plot, which is going to verify the same. So we have applied, as Professor Yadav has shown us, we have applied various chaotic transform, just like a node map where x, y are the pixel of original image and x prime, y prime are the pixels of transform domain. This is also known as node cat map. Basically, after first iteration, we'll get image which is second one, and after few iterations, we'll get a random image.
Dr. Kehar Singh, please finish in 1 minute.
Okay. So this is a fine transform. This is a logistic map. This is the Lorentz map, Tinkerbell map, Hannon map. And if you want to see more chaotic maps, then you can move to here. So I'm just giving you an example how we implemented chaos in the optical imaging. This is the standard double random force encoding scheme, where in the frequency domain we have made system as chaotic by using any of the chaotic map which we have described. I just want to tell that we have proposed a new map, which is umbrella map, which is based upon the Tinkerbell map. And this is the bifurcation plot, which looks like an inverted umbrella. And it's a Lyapunov exponent. If we compare with the original Tinkerbell map, it is quite high. Also, there's a paper published in Nature, which give a more convenient and faster algorithm to detect chaotic behavior, which is based on chaos decision tree algorithm. This also confirms that this map is chaotic by the K values. These are some results, validation results of the scheme which I discussed in the previous slide. The difference between the classical optical schemes and this is the histogram, where you can see that histogram of the encrypted image is quite flat and it reveals no information to the attacker. And these are the occlusion as well as noise results on the image. And these results are of the deviation of the parameter. Let's suppose if a person don't know the 6 parameter of this umbrella map, so they are as sensitive as 10 raised to power minus 15. So the computation cost for getting that apply for brute force attack is quite high. So therefore, we think that through mathematics, or we can apply the chaotic map with the optical schemes, so we get a better secure system. These are the references, and once again I'll thank the organizers to give me this opportunity, and happy birthday, sir. Thank you.
Thank you, Dr. Kehar Singh.
Yes.
Any comments or questions? You can unshare the slide, please.
Yes.
If not, we will go to the next speakers. We have Dr. Aloka. Aloka is our colleague from the Delhi Physics Department, and after her PhD from IIT Madras, for joining faculty, she will spend time. Aloka?
Yeah.
Yeah, thank you.
Okay. Thank you, everyone. So I was very happy to see that the work related to chaotic maps has really moved on. But today I will not be talking about chaos and encryption. I have also moved on with my research area. So I will be talking about liquid crystalline system, and the topic that I have selected is when life gives you LCs, tune it. So liquid crystals, as all of you know, is a phase of matter that is in between the crystalline phase as well as the isotropic liquid phase. So it has an order which is in between these two phases, and liquid crystals have been extensively studied. They have been widely used for displays, but they have some emerging applications. These applications are in the area of adaptive optics, telecommunications, photovoltaics, and sensors. So there is a requirement of specific properties which have to be tuned with respect to these applications. So the main topic that we will be discussing today is that we will try to tune the properties of these liquid crystalline phases to the specific applications. So first I would begin with a talk related with some novel systems. So here we have what is called as liquid crystals, which are widely used for various kind of display devices. But all these display devices are mostly based on pneumatic LCs. These pneumatic LCs are rod shaped and they inherently lack polarity. And because of the lack of polarity, what happens is that you have a large switching time. So what is the way around this? So what we try to do is that we try to bend the rod. So how do we do that? So this is a typical calamitic liquid crystal. This can be bent, And because of bending, what happens is that we come into the region of what are called as bent core liquid crystals. And these are the materials for the next generation displays. So why study bent core liquid crystal systems? We study the bent core liquid crystal system because they show ferroelectric nematic phase, and this would result in faster displays, and finally this will be the reason for the next generation displays. Now, what are the challenges? The challenges with these systems is that we have to understand the effect of the molecular structure. We have to realize the polar electric nematic phase, and most importantly, we have to get the room temperature nematics. So here we have one of the typical system that has been studied. As you can see that it is a 4-ring system, and this is characterized by using both the differential scanning calorimetry as well as polarizing optical microscopy. And because of that, you can see that a Schlieren texture can be seen in the system. So this is a dielectric spectroscopy study, and because of this we see that where we have studied the dielectric constant as a variation in frequency, and here we can see that there is a what is called as a low frequency relaxation peak, and this suggests a collective mode. So how do we understand the occurrence of such a collective mode? We can look at the bend shape of the molecule. This is a typical structure of a bent core liquid crystalline system. This will result, because of the shape of the molecule, it will result in short range ordering. And this short range ordering is called as the cybotactic groups. Then we have what are called as layered domains. And these layered domains on their own are polar cybotactic groups, but they are randomly oriented. So what happens because of this is that you have a macroscopic polarization which is equal to 0. Then we have to apply an external electric field, and because of the application of the electric field, what happens is that you have a transition to the ferroelectric state, and this is what is confirmed by dielectric spectroscopy. Recently, we tried to model the cybotactic clusters because the utilization of these bent core system is predominantly dependent on understanding how the cybotactic clusters work. So we have tried to use the famous Landau-Diegens model, where we have tried to couple the molecules and the cybotactic clustering, and because of that we have understood that there is very limited effect of confinement. Further, we have also studied the effect of quantum dots on these cybotactic clusters. So the major conclusions from this kind of study is that the boundary conditions have a very weak effect on the cybotactic clustering. Definitely there is a reduction in cybotactic clustering due to the incorporation of the quantum dots, and this can be further explained by reduced birefringence as well as orientational order, but there is an increase in what is called as the increase in activation energy. Now I would move on to some other interesting topic that we are trying to study. This is what you call a composite of polymers and liquid crystals. So what are we trying to do with polymers? If you try to tune in with polymers and liquid crystal, we can generate what are called as energy harvesting devices. We can have smart glass windows, as well as they show faster response. So the various forms that we are trying to study, one is what is called as a polymer dispersed liquid crystals. So what are these polymer dispersed is that the liquid crystals are dispersed in these polymers, and therefore we have what are called as polymer dispersed liquid crystal. The other mechanism is what we try to call as polymer stabilized liquid crystal, where we try to stabilize the liquid crystal system by the use of polymers. Recently, we have some very interesting results. where we have tried to generate what are called as polymer-filled liquid crystal, and they are designed using amino acids. Amino acids are very important because they are biodegradable, and this has been done by using the SORB method, which is a very simple technique. And because of that, what we have is that in the what you call the liquid crystals, we have what are called as polymer balls. This results in a device which shows very good transmittance, but at the same time, the threshold voltage required for such transmittance is very limited. I would now move on to another interesting topic. This is related to liquid crystal waveguides. And all of us know that an optical waveguide...
Aloka, please finish in 1 minute.
Yes, and it is based on what is called as total internal reflection, and here these optical waveguides are used for integrated optical circuits. So basically liquid crystals are used because they are highly birefringent, and they can be used, the electric field can be used to change this birefringence. So this is one of the typical structure that we had designed in our lab earlier. Recently, we have made other devices which are LC cladding waveguides, which work equally well. Here the core is the polymer. And we also have designed what are called as periodically segmented waveguides. These can effectively work as mode size converters. So there are further work that is going on in the lab. These are to do with basically pressure sensing using liquid crystals, gratings. We have designed very good cellulose-based diffusers. We are also looking at magnetic ferrofluids, energy harvesting devices using liquid crystal, and at the same time designing what are called as ion-rich as well as ion-deficient system. Finally, these are my collaborators, and finally, I would like to wish from the group a very happy birthday to Professor Kehar Singh. He has been an inspiration, and always whenever we have to talk about literature survey, which is always incomplete by most of the students, I always quote that we had to do quite an extensive literature survey under the guidance of Professor Kehar Singh. Thank you.
Thank you.
Questions, please.
Thank you, Professor Aloka. Open for 1 or 2 questions. Okay, so thank you, Professor Aloka. So we'll move on to the next speaker.
Okay.
Dinesh Ganatra. Dinesh. Yeah, we have Dr. Dinesh Ganatra, who is did his PhD with Professor Kehar Singh and myself, and he is associate professor IGDTUW. Thank you.
Thank you, Professor Jovi. Without wasting much of the time, I straight away start with my presentation. First of all, many happy returns of the day, sir. The 80th birthday. Can you see my screen?
Yeah, it's fine. Yeah, go ahead.
And I'll be talking about advances in image processing. Just one part of it, I do research on this, and not the entire one, but okay. This is one of the picture in which I'm there in the lab, the applied optics lab, the way it used to look like, the files behind, the one on the left, and the picture in the center is Professor Kehar Singh. This picture I took, I think, when I was in Italy, my first ever visit abroad, and Professor Kehar Singh is with Cornelia Dance, professor in a German university. Okay, and the picture on the right, this is there again me with Professor Naveen Nishal. Okay, the picture on the right is special, and why I have included is because this was the first ever picture that was taken by a mobile phone. At that time, me and Naveen were, below that main building, and I was not knowing that this picture can be, transferred to the email, and I was quite surprised to see that even a mobile phone can take a picture, that to a colored picture of such a good quality, and it will be transferred to our email, and we can, process it further and do some image processing on it. So that was perhaps the initial stages where people started taking picture with mobile phone, and there were no applications, or there and now if you see that a sea of applications are there, and a lot of commercial activities have gone on the pictures taken through mobile phones. So we in IIT were the first one to be exposed to such kind of technology, but we couldn't apply this for some commercial use, or but we were the first one to be introduced to the technology. So somehow we are missing that link where, even though like we are exposed to the technology, but we don't apply them for the commercial use. Okay. Coming back to my research, part of it is related to this neural networks. So this is one of the applications which, as I was, the topic suggests that I'll be talking about advances in image processing. So the recent advances has been, application of image processing through this deep learning and deep neural networks, and as you can see, that automated driving and all these things are coming up. Then this convolution neural network is used in this deep learning, and I'd like to thank sir for this, that sir had I had introduced these neural networks in optics way back in '98, and now people have started using it. So it's been an advantage for me that I had already gotten experience for all this. Then this scale invariant feature transformation, this SIFT transformation was we used to study it for image processing, but now it has become actually a tool in MATLAB. It's actually a function in MATLAB that people use, and this was earlier introduced by someone else, and MATLAB, as I have seen, I started working with version 5 of MATLAB, and over the years, whatever tools that we used to access earlier, which were not part of MATLAB, but some research group has developed them for their own research, now they are there as a product there in MATLAB, as in the toolbox. So how all these technologies have evolved and have actually been utilized by these giants, the technology giants, and I have seen this with my own eyes, and I still feel that we too could have done something similar and made some software like these, and made some products like these. Then another advances in optics which has taken place is this maximally stable extreme regions. As you can see that we have applications for, let's say, counting the number of cells under a microscope. So we have these automated algorithms to do this job very efficiently, and now this has actually become a textbook subject. So the pioneering book in optics, the Gonzalez and Woods, have got these as the textbook topic. So whatever that we used to study as research is now there in the textbooks. Again, I still remember there was some MTech thesis by IIT Chennai, IIT Madras at that time, where the snake algorithm was there, and sir has given me that thesis to check that, and now this has become a textbook topic. So how the advances have taken place is something that is wonderful to see. This K-means clustering, one of my research scholar was working on it, and now this has become a textbook topic. Then, of course, K-means clustering has been there in literature for a while, but then use of it in optics is something, or image processing is something which is now there in MATLAB as a separate function. Then histogram matching, because nowadays we need to have certain smart cameras which are, say, let us say, on the surface of Mars, where they need to do some image processing on their own, because the signal will take very long time to come back to Earth, and if we try to intervene, it will be too late. So these things are done at the image processing level on board with the onboard computing on the cameras themselves. Apart from this, another advantage is the advances which have taken place in optics is like you can convert such black and white images to color images. And look at the image; it's been so smart, as though some humans have applied those colors, but no, it's done entirely with the help of image processing and computers. And another advance which has taken place is in this the hardware part. These companies like NVIDIA, Intel, Qualcomm, AMD, they have come up with both hardware as well as software. Hardware in the sense that they have a separate what do you call this, CPUs, sorry, the GPUs, which though you might say that the kids use this for these games, but no, that's not the case. Even the image processing industry uses these for their advantage, where the image processing is pretty fast and it's parallel. In fact, some of these companies have got their own APIs, like CUDA of NVIDIA. Even Intel has its own application program interface, which gets integrated, and that makes the computation, the image processing computation pretty fast. Then over the years, we've been using JPEG 2000 as the file format for image transmission and even for image compression or video compression. But now Google has come up with this WebP file format, which almost.
Dinesh, will you please finish in 1 minute?
Yes, sir. I think this is the last slide. Okay. Okay, so that's all I'd like to share with all of you. Many happy returns of the day, sir. Apart from the pictures that I had shown, I have one more thing to show here in the video, if all of you can see. So this is, so can you recognize this?
Actually, you are, okay. I have to highlight your, sir.
I don't know whether Professor Kehar Singh is there in this. Anyway, the meeting is being recorded, so he can see it later. So this was.
I think we can see now.
He had given me when he had come to my marriage, so deserved even the currency first. so now that I have my own research scholar, so I can understand the love and affection that one has for your own research scholars. So it's a wonderful relationship, and I'd like to I'd like to wish him that he has a long and healthy life and a productive life for many years to come. Thank you very much.
Thank you, Dinesh. We will. Have anybody has any question? Okay, thank you, Dinesh. So we will go to next speaker, that is Professor Naveen Nishal from IIT Patna. Naveen. Yes, the slides were visible, Naveen. Now they have disappeared. Yeah, that's fine.
Okay. Very good evening to you all. On this occasion, first I wish to a very good happy birthday to Kehar Singh sir, and we wish that keep blessing us for a long time. So the topic which I have chosen today to talk about is the optical cryptography. I learned this working with you, sir, and I am continuing my work in this area. So today, quickly, which I am going to discuss is about an optical crypto system and quick response code-based crypto system with low-cost light source and a vector beam-based system. So coming directly to the topic, that in optical cryptography, we deal with the systems where we get degraded output images after decryption of the data. Once we follow the double random phase encoding or any other encoding process, whether symmetric or asymmetric crypto system, in actual optical cryptography, when we deal with the experimental results, we get the degraded quality of the output results. So our main emphasis was how we can improve the quality of the degraded, decrypted images, and also in dealing with those data, we use a laser beam to encode that information. So laser introduces speckles. So how we can replace lasers with a low cost light source that will finally bring down the cost of the actual actual practical system. So quality degradation, with the issue of the quality degradation, we use this QR code based system, and in this case we have used an LED light source, which is a low cost source, partially coherent illumination, and we applied this quick response code, which is a very famous thing. So we implemented with the two SLM based system. We have to match the pixel by pixel matching of the two SLMs, and then we can record that. So these are some of the results based on that, where plain text has been encoded into a QR code, quick response code. This is the encryption key, and this what ultimately the encrypted image will look like. And we successfully decoded that with the three different LED sources and also with the laser source. And we found that with the laser source, like the right the bottom corner, you can see it is with the output with a laser of 532 nanometer wavelength. In this case, we could see the speckle patterns and that it was a noisy pattern. On the other hand, with white LED and with the green LED, the results were much better. We did some numerical parameter computation also to validate that. Further, we applied the same algorithm or for the same system to encode a colored image, and in that case we wanted to increase the security of that part. So we applied the polarization based component, and the polarization based principle has the benefit that we can record only the intensity, so we do not have to deal with the recording of the phase. So recording of the phase requires interference based technique like holography, or you can use any digital holography or any other concept. But in this case, we moved from the holography or interference based technique directly to the polarization based technique and applying the incoherent source of light and also with the colored image. So I'll not go into the details of this algorithm, but I'll show you some of those results, some simulation results for the colored image. So we have to actually break into the red, green and blue color component. So one of the components result I'm showing here. You have to encode it in a QR code. QR code is basically a black and white picture. So it takes less memory. So in a way it solves the problem of the storage also. These are some of the experimental results with the same concept, where we have applied the concept of polarization and LED light source with the aim that how we can improve the quality of the decrypted image, make it a low cost device, and also how we can move from the interference based technique to directly recording of the intensity patterns. In order to further strengthen our system, we moved to the concept of the vector beam, which is basically a spatially variant state of polarization. Scalar beams and vector beams. Scalar beams are basically it has uniform state of polarization. On the other hand, vector beam has the spatially variant state of polarization. So this vector beam concept was applied. In this case, we can generate a key for securing the information. Now in this case, these are the algorithms how we have developed and moved into that concept. I'll skip some of those parts and also the mathematics part. What was important here, that in this case we have to encode either of the two images. So you have the X component and the Y component. We have to deal with both the components while encoding the information. And then you have to process that and use the Stokes polarimetry to record that intensity information, and that helps the storage process, and there is no compromise in the security of this system also. In this case, we felt the problem that we have to encode the X component as well as the Y component. So we were looking for an alternative that how we can arbitrarily encode the vector beam. That will be a better solution to this aspect. So this we used for not only imaging, for the authentication process also, and this is what is for the authentication of the information. So in addition to moving from this concept, we moved to the arbitrary vector beam concept, that how we can arbitrarily encode the information. I'll skip these results. These are the for the authentication purpose, whether you have to check the authenticity of the data, whether it is authentic, yes or no. So you have to true class object and false class object. We have to separate them, and then you can look at the correlation output. These were combined. Recently in this paper, what we have combined, we did with the arbitrary vector beam encoding. So in the previous problem we solved in this case, that we don't have to encode this X component, Y component, and we can arbitrarily encode this. And this we implemented experimentally. The preliminary results are shown here. They like 1, 2, 3 are the plain text, and we have to encode them in this vector beam. This is what the decoding scheme is, and these are some of those results with this arbitrary vector beam concept. So I think with the paucity of the time, I cannot explain everything, otherwise it will take longer time. So two ideas we were working on, that removing improving the quality of the decrypted image, and second problem we have to deal with, that how we can deviate from the interference based scheme, so that we don't require storing phase information. Polarization based concept on the vector beam concept, we can record only the intensity pattern, so that's a good deviation. And so I must acknowledge my students who have contributed in this case. And in nutshell, I have last year I have authored a book which is optical crypto systems. So many of you, whoever is interested, he or she can read this book. If you need, I can share a soft copy of this book with you.
Sir, please do share the whole soft copy. Actually, we have it in chapters.
Yeah, you have to send me an email. I'll send you the whole book.
Okay,
so
sir. Thank you so much.
And one of the pictures I thought of sharing. It is I got a memento from sir in the iCall 2019. So thank you very much.
Thank you, Professor Naveen. And any questions, please? Kedar?
Yeah, so Naveen, is there a special way to handle SLMs with vector beams?
No, not a special way. You have to display the CGH. You can display the CGH and you can generate them. There are many other papers I did not discuss here, how to generate the vector beams. So initially we worked on the generation part, and then as a later part we did it for the application.
No, what I was that SLM responds to only one polarization. How do you handle the vector beam?
There are various ways to deal with that.
Okay.
Yeah, if you wish, I can share you those papers.
Okay. I have to look up.
Yeah.
Okay. Thank you. Okay, thank you, Naveen, and please unshare your screen. So we will now move to Professor Renu John from IIT Hyderabad. Renu. Yeah, it's fine. Please go ahead.
Am I visible?
Yes, well, okay, go ahead. Thank you.
Yes, so, very good evening to all of you. Happy birthday to my professor, Professor Kehar Singh, sir. Today, I will quickly give an overview of holographic microscopy and other quantity phase microscopy and its applications in clinic, where we are using it for diagnostic imaging applications. So traditionally, when we look at microscopes, the modern microscopes are really expensive with a lot of sophistications and complexities in its hardware and optics as well as in the software part. So when I talk about smart microscopes, I really mean microscopic systems that are quite portable, where the diagnosis could be at your doorstep, at your home. The power of computation and imaging could be combined so that you can take decisions, diagnostic decisions at home or at the click of a button, and also devices like handheld devices which could really enhance the imaging capability of systems with the power of computation. So when I talk about intelligent systems, AI and machine learning have been everywhere in every aspect of human life, right from your mobile phones to all other applications of your shopping, etc. So why not in clinics? So artificial intelligence has been very important in taking decisions, especially clinical decisions when it comes to diagnosis. You can really augment the skills of a clinician. Rather, you can really share the cognitive load of clinicians to take decisions with the help of artificial neural networks. So with the availability of large amount of data in electronic form, you can really we can really empower the patient to be part of the diagnosis process, like taking images even using mobile phones. And the whole decision happens at the press of your mobile phone button, where you could really take decisions on treatment, on type of disease state conditions like cancer, etc. So this has been possible with the advent of high performance computing, cloud computing, and AI. So we talk about when we talk about microscopy and 3D microscopy as such. So traditionally, when people used to look at cells in the lab or a pathology lab, they used to look at cells which are collected from the patient's body. They undergo a long process of staining and fixing and looking under a microscope for identifying the pathology conditions. So in case of quantitative phase microscopies or holographic microscopy, for example, so we do see the entire cell without any staining or fixing, and you can really look at live cells. And the whole 3D volume information of the cells is available for you for diagnosis. So this is much more effective in taking decisions without any long and cumbersome process of staining and fixing. So these are examples where cells from the oral cavity were used for oral cytology for cancer diagnosis, image using a holographic microscope. So you can see that the column at the left corner, left is regular histopathology where the cells are stained and looked at a microscope, and we can see the whole row of whole column of cells where you can really 3D phase and quantitative depth of cells. And these images are very clear in showing the volume information, and you can actually find out the nuclear to cytoplasmic volumes. And what you see on the right side are clearly precancerous cells from the oral cavity, where the nuclear content is pretty high compared to the cytoplasmic volumes. So this is yet another example where holographic imaging or 3D imaging comes for applications like characterization or morphology of human spermatozoa in vitro fertilization applications. So typically, if you look at the sperms for characterization, there are more than 80 classes of anomalies of sperms, which render them infertile. So to understand the morphology of sperms, all of these cells have to be collected, stained and fixed and looked under a microscope, which is quite cumbersome and taking a lot of cognitive load on the pathologist who is sitting behind the microscope. So one single holographic microscopic view of a sperm cell would be like this. where you could really see the 5 micron thick head of the sperm, the anomalies that could be present at the tip of the sperm head, the mid piece of the sperm, and way up to the tail, you can see about 100 nanometer thick tail of the sperm. So this is the capability of a holographic microscope that can deliver 3D view of the live sperms without any staining or fixing. So we have worked quite a lot ahead on this with an in vitro fertilization clinic, and these imaging modalities getting translated to the clinic right now. So I would like to wrap up my talk with 2 different applications. One is based on deep learning assisted microscopy, where we can do an intelligent and automated classification. And the second part, I want to highlight how deep learning could come in reconstruction or amplitude and phase reconstructions of cells. So this is again the same example of sperms where we could put classification algorithms to classify the sperms as normal and abnormal, and also you could find out decisive clinical parameters like the nuclear volumes, the cytoplasm volumes, the shapes and contours, etc. We could also try looking at retrieving the face of cells or images from a stack of intensity images using the principle of transport of intensity equation and plugging in something like a GAN network. So a stack of intensity images is plugged into the deep learning network, which could give the 3D face and amplitude of the object. So you could this one of the simplest example where you could do a face retrieval with the help of a deep learning network. So we also tried looking at reconstruction of face with the help of networks, deep learning networks, where we could really plug in the physics of hologram formation. So we in this particular model, we were trying to look at a regularization-based denoising algorithm plugged in along with a deep learning approach for reconstruction of face. So this work is currently in progress. So with this, I would like to wrap up my talk, and thank you very much, and thank you, Professor Kehar Singh. We all of your students are deeply indebted to you for your guidance and for teaching us to think independently, and you showed us the importance of hard work. Thank you for being a great mentor. Thank you, Professor Kehar Singh, and wish you a happy birthday. Thank you very much.
Thank you, Reno. Any comments or questions?
Yeah, just one.
Yes, sir.
Query. You must have seen paper in optics letter by Professor Javidi.
Yes. Yeah.
I also sent you the link.
Yeah, you shared with me. Yeah.
Right. So how do you compare your technical capabilities or technical capabilities of your lab with the level that that paper has attained?
So this was, if I remember, this was a deep learning network for face reconstruction, right?
Yes.
Yeah. So I think there are a wide classes of neural networks and deep learning networks being tried for various applications. Of course, image classification is an old problem, but face retrieval is something where people are revisiting traditional face retrieval algorithms with the help of a learning or learning networks. So I have used 2 different models for learning. At the same time, what is missing is that we know that when light diffracts, there's a kernel, which is the Fresnel kernel that is propagating. How can we plug in the physics of it into the learning network so that reconstruction can be better? So that is one of the challenges. I think so far most of the work is really agnostic to the physics of it. So they are plugging in a different neural network model and trying to retrieve the face.
And his device is very compact, you'd say, handheld.
Yeah. So most of these we have now lensless images, which is nothing but just a detector array, and we can do decent 3D reconstructions of cells. It is almost like you can prick your hand, take a blood smear right on your mobile phone camera, and you can retrieve the 3D face image. It's very close to that. So it's not just a regular mobile phone camera. We really remove the lens and make it lensless.
Okay, thank you.
So we have 2 more questions, Dr. Joshi and then Dr. Kanik Paloti.
Hello, Renu. It's nice talking to you and seeing you after a long time. Just a small question. Is there any work done on COVID also at your end, or is there any update on that from your side? Thank you.
So we do work on COVID, but not on optical methods. We are working on an electrochemical sensor where we could really look at the COVID nuclear capsid proteins. The sensitivity is an issue. We were not able to get the sensitivity as is reported by the commercial kits.
Thanks.
The paper is concerned with COVID, Javidi's paper.
Yes, yeah.
So you can send the information to Madhusudan.
Yeah, sure. I will share that, Joshi. I have that paper. I will share with you.
Or I can share with them.
Okay, Kanik Palothi.
Yeah, hello sir, and thank you for the organizers to have such a beautiful way of celebrating birthday. I think most of us are sort of new to this format, and I wish all the best to all the organizers because personally, first of all, happy birthday, sir, and also I think. I'm sorry, I'm making a longer comment, but I think in India, we do not celebrate the birthday of our academics, our scientists, and as I feel that we cannot create, science is a field where there is no second prize. So those who have at least achieved something, we should be celebrating, otherwise our younger generations are not going to, sort of portray us in the same manner. With these words and also extending my happy birthday wish to Professor Kehar Singh, I wish to have one small question regarding phase retrieval using GAN, whatever you have mentioned, sir, Professor John. Actually, in adversarial network, there are two sort of separate wings who work together in an adversarial model. Here, whether this the reference part and the other part of the object, they are working in a separate domain and then finally trying to match up, or can you just give us a little bit of insight how this is phase retrieval is done?
I think it carries a longer discussion, but of course both parts have to be combined. But there are also disadvantages in using GAN for phase retrieval because there has to be one-to-one collection of data set to reconstruct, which is one of the main drawbacks in GAN. We can talk about that a little bit longer. We can
yes, definitely. Okay. Thank you so much.
Okay, thank you very much, Professor Renu. We will move on to the next speaker, Professor Rakesh Kumar Singh.
Sir, can you permit me to share the slides because I don't have permission?
Oh, really? Let me just check, Rakesh. No. Yeah. Okay, please do that. It will work now.
Are you able to see the slides?
Not yet. Yeah, it's coming. Okay.
It's coming?
Yes, please go ahead.
So in the beginning, I would like to wish Professor Kehar Singh happy birthday and also thank organizer to share my very recent work. I intensely selected this topic. I learned a lot from my both supervisor, Professor Senthil Kumar and Professor Kehar Singh, and on the orbital angular momentum and light with what we call the LG beam or vortex beam. So here I am going to share our work where we combine the computational optics and correlation theory to develop a new method for OM reconstruction. And when I say OAM reconstruction, or orbital angular momentum state reconstruction, I mean to say we are going to reconstruct different modes. So as we know that any we can in certain cases we can decompose information in Lagrange-Gaussian modes, or in we can say the helical mode, and our objective is to decompose these modes through the scattering media. The question is, why do we want this kind of work? So I will explain in the coming slides. So this is the introduction of my talk, where I will explain why do we need the OAM or vector states, particularly though we work in different domains like ghost imaging and single pixel imaging, but here I'm going to talk only on the application of correlation optics for OAM reconstruction. So similar kind of and the basic principle is derived from the ghost imaging technique. So we know that the OAM beam, or what we call the vortex beam, is commonly used in free space communication applications, and the reason is that this kind of beam can carry lot of information in comparison to the beam encoded with the polarization states. So majority of works in this domain are going only in the free space communication, where you don't have any random scattering or turbulence, or usually they ignore the turbulence strength. But in case of small distance communication, where you have the severe problem of scattering medium, or you want to communicate the data through the random scattering medium such as a wall, then how do you communicate, or how do you build a system for free space communication system? And here the role of OAM beam or OAM modes can also be utilized. So earlier Professor Senthil Kumar nicely explained the idea of OAM modes and different applications. So I'll briefly tell what is the orbital angular momentum modes, which are usually theoretically explained as a solution of wave equation in paraxial condition under cylindrical coordinate geometry. There are several ways to generate the OAM modes. Some of the generation techniques I have explained here. Now, and nowadays these OAM modes are now they are also working as a link between the quantum inspired imaging, because when you see the recent trends in imaging, advanced imaging, people are trying to combine, also try to explore the close connection between the quantum and classical imaging systems. And OAM modes imaging systems have given a lot of directions to explore this subject. So one of the possible connection is the ghost imaging, where this kind of entangled, whether classical or quantum entangled sources are being explored for the unconventional imaging system. Okay, so this is the problem statement. So in the conventional free space communication system, where people even use the OAM modes, they consider the free space. But now I'm posing the question that what will happen if your beam, which is carrying information, or we can say your beam decomposed into OAM modes, propagating through the scattering medium. Usually, traditionally, if you use the traditional method or traditional even holographic method, I will try to connect this with holography. So here I'm saying traditional conventional holographic method. So what you will get only random pattern. So it depends on how fast your randomness is fluctuating. Here I am giving only one fluctuation for sake of simplicity. But if you have dynamic situation, you can have the very high speed detector, and then you can perform the experiment. So what you are going to get, you are going to get a speckle pattern. Now the question is that, can we get information of OAM mode from the speckle pattern, and without any imaging device, in lensless configuration? So we are going to answer this question. And why OAM? I already explained that we can encode our information into a combination of OAM modes, and once we decode the OAM modes, we can reconstruct the object. So to develop such ideas, what we do, we try to utilize the knowledge of theory of coherence, which is a contribution of Professor Emil Wolf is very significant in this direction, and Professor Kandapal is here. His contribution is also significant in this area. So what we try to do in this work, we try to utilize the knowledge existing theoretical framework of the coherence theory to build a new imaging system, lensless imaging system, to get the OA modes. And uniqueness of our imaging systems is that it's a lensless, you can say self-referencing, so it's highly stable. So I'm going to explain how do we do this. So for this purpose, we developed two techniques. The first technique was reported in 2016, where we tried to build a holography with Henry-Brown twist approach. And if you see the literature, Henry-Brown twist experiment was done for different applications. It's for to measure the size of the star, and that was for different reason. But if you go for conventional Henry-Brown, the problem is that the phase information is lost, because when you do the intensity correlation, higher order correlation, the phase information is lost. Only you get the modulus of the Fourier spectrum. So to overcome this problem, we propose that we can use a homegrown random field, and before taking the intensity correlation, let us allow these two random fields and interfere like speckle interferometry, and then do the intensity correlation. So this intensity correlation, you can say, is Henry-Brown for polarized light. So it's a Henry-Brown is extended to polarization domain. And another advantage is that we also got the phase information, which was lost in conventional Henry-Brown twist approach. But in the first setup, the disadvantage is that we need another separate, just like off-axis holography, but is holography with a coherence wave. Please remember, this is a different kind of holography. It's not conventional holography where you use U1 plus U2 and take modulus. Here we are interfering complex coherence function and then making the hologram. So it's a hologram of the coherence waves rather than the optical field. And once we reconstruct this coherence hologram or hologram made by the coherence waves, you can get the information. But this is unstable because you need another separate beam. Very recently, this paper is in second diagram. This is in the review. We try to realize this idea by using the higher order Stokes correlation. So what we did, we know what is Stokes parameters. So this is our idea. So you have the light carrying the OA mode, which carries the information of the object. Here I gave only one mode, but later on I will also say.
Rakesh, please finish in 1 minute.
Yes. So in this case, using this setup, you measure the Stokes parameters, and once we have all 4 Stokes parameter, you do the higher order Stokes correlation, like correlation of the Stokes parameter between 2 points. So you have Stokes parameter 4, 0, 1, 2, 3, and then correlate. And once you have the combination of these Stokes parameters, and this is experimental setup, we divided the beam, imposed the certain information in the OA mode by the cell length, and then we measured the Stokes parameters using conventional Stokes polarimetry technique. So we got the 4 sorts for different orientation. And once we have the speckle pattern, we do the correlation, and after processing this correlation function, we can see here, you can see here, we have the vortex structure. So even from the speckle, in the completely, you can say, completely highly stable interferometric setup with self-referencing, we got the vortex mode, and there is no lens. So even if you're far away, long distance, you can do without any lens, without any imaging device. Here I will also like to share that we did this experiment for combination of modes, and you can see by using the mode projection, we demonstrated that whatever the modes you have, or whatever the modes involved in your beam, you can decompose and read the information. So with this, I would like to conclude. So we have developed a new imaging technique, and our application is to reconstruct the OA modes of the light. With this, I would like to thank the organizers.
So, thank you, Professor Rakesh. Any questions? You can unshare your screen. Okay, so if not, we will go to the next speaker. Yeah, there is somebody who's.
Yeah, there is one question, sir.
Yeah.
Yes.
Yeah. Rakesh sir, I was just wondering that whether it is possible to like recover the OM using wavefront shaping technique like transmission matrix method, Can it be
Okay.
used
So
for
yeah,
unscrambling the
good.
waveform?
Yeah, so you can do, but that is if you go to transmission matrix method, depends on how many modes you are able to measure, right? So you have to, for one orientation, you need to measure the transmission matrix. For another orientation, if your beam is misaligned, you need another transmission matrix, and that is very time consuming. Another wavefront sensing will not work if you have multiple scattering. Here this in this case we have considered the multiple scattering. So if you have multiple scattering, you can't use the usual adaptive optics approach.
Okay, thank you, sir.
Kedar?
Yeah, so Rakesh, the signature of OAM is there in the center of the correlation pattern, is it? Where is it exactly?
Okay. Yes, in the center, but we can also, depending on like we have the two coaxially beam, so it can be also off axis. So you can measure anywhere. It doesn't matter that you need only at center.
Okay, so thank you, Rakesh. We'll move on to the next speaker, Dr. Anit Nelleri.
Am I audible, sir?
Yes, please.
Thank you, sir, for the introduction. Good evening to all of you present in this meeting to felicitate Kehar Singh, sir, on his 80th birthday. My association with Kehar Singh, sir, goes back to the beginning of 2000, when I started working towards my PhD under his tutelage. It is largely due to his association that my mind got deeply entrenched into the field of photonics. I sincerely wish Professor Kehar Singh, sir, on his birthday and pray for his continued good health and cheer. I also wish that my association with him should continue in the years to come. Happy birthday, sir.
Thank you.
Thank you, sir. Today I'll be giving a brief introduction about the compressive digital holography, which we've started recently, 1 or 2 years ago. And holography is a well-known technique which records the wavefront. When the emergence of digital holography, which is termed as coherent optics of 21st century, with the development of very good sensing technology and high computational technique, fast computational techniques, which gives the computational degree of freedom of processing both intensity and phase, that is the complete wavefront using a computer. And fast recording is possible, and transmission of 3D information through internet is possible, and all sort of image processing algorithms can be used for processing the 3D information, because 3D information is obtained in the form of a digital complex image, and by processing 2D complex image, we can process 3D information. Now, let me give a brief idea about the compressive sensing. This compressive sampling is a paradigm shift in signal processing. So if you want to reconstruct the signal faithfully, the highest frequency of the signal, the sampling frequency should be much greater than the high, or the highest frequency should be sampled twice. So and the linear measurements in a compressive sensing, the linear measurement m can be much less than n, and this is not a magic. This relies on the sparsity of the signal. Sparsity is the number of non-zero samples in the signal. The signal is S sparse, and if there are n non-zero samples, so the CS requires m linear measurements of a signal dimension n to reconstruct the original signal from the measurements. So this is the idea. Now I'll talk some mathematics behind this. See, let us assume a linear mapping y is equal to psi x. So x can be found from y. This is a linear inversion. If the measurement is incomplete, then this is not straightforward. So we have to go for an optimization. And that optimization is the complex unconstrained optimization. So this is the way we minimize the norm we use L1 norm because the sparsity is optimal, so we go for the L1 norm optimization. And this is the if the signal is sparse and the equation 4 is obeyed, we can go for this convex unconstrained optimization problem by CS method. So this is a sparsification method, and if the signal is not sparse in transform domains like in spatial domain or its transform domain or time domain or its time frequency domain, we can use a sparsifying matrix. X is equal to phi x, when phi is called the sparsifier, right? So psi is called the sensing matrix. So this is the way we can sparsify and get a better resolution. This is an inline single-shot digital holography. We'll discuss some practical problems in implementing the CS. In inline single-shot digital holography, we have object beam and reference beam are interfering in inline geometry. The angle between them is equal to 0. So it is when you expand it, we will find some nonlinear terms. When we apply compressive sensing, we assume that because compressive sensing requires a linear sensing matrix, because the nonlinear terms are ignored, considering it has a model error. So the intensity may get reconstructed perfectly, but the phase may not be, because most of the papers they don't discuss about the phase reconstruction, but intensity will get unaffected. This is the same problem we find in complex off-axis single-shot digital holography also, because nonlinear terms are present, and when reconstructed, we have to consider the nonlinear terms and model error, and then we have to go for a compressive convex optimization. And there is a linear approach. We can use classical phase shifting digital holography, in which we have to record multiple holograms. Multiple holograms we have to record. But one drawback, because of the linear problem, multiple holograms are recorded, and in the recording plane, the Fresnel field or the Fresnel transform of the object field is retrieved, and it is inverse transform, because it's almost linear problem. But the practical difficulty is when we are recording multiple holograms, if the specimen is moving or dynamic, we cannot capture the events. So this is a practical situation. Now, a single-shot parallel phase shifting holography is one solution. Parallelly or in an interleaved manner, we can address the phase shifting, and we can separate out 4 holograms from one single detection. And in the 4 holograms, we find that there are certain pixels 0 value, and we can call it as a loss of information. And the same classical phase shifting formula can be applied on these 4 holograms, and the Fresnel field can be retrieved, and the further compressive sensing can be applied, because in each hologram there is a loss of information. So this loss of information can be corrected by compressive complex optimization. So this is the conventional hologram reconstruction. Object field, because this is in perspective of parallel phase shifting or in phase shifting holography. Objective field, and it is Fresnel transform. It's a free space propagation. I call it as Fresnel transform. And the Fresnel field is interfered with the reference wave, and Fresnel field is retrieved and inverse propagated. This is a conventional way of reconstructing a phase shifting hologram. And in convex optimization, in compressive sensing, we are retrieving this information from this and from the hologram, and that information we consider as an incomplete information. And that is a sensing matrix. Sensing matrix consists of object field, Fresnel transform, and holographic. The entire thing comprises of the sensing matrix. And sensing matrix gives an output of hologram, and from that hologram we can retrieve the Fresnel field. And from the Fresnel field, we can do this complex optimization. By iterative search, we can reconstruct the object field pattern. And
please
this
finish
is
minute. Please
yeah. This is the object we used in phase shifting geometry. And even with the 50% of the pixel, in the conventional method, we are getting a resolution fall like this. When with using 50% of the hologram sensed data, we are able to get with a B-spline specification, and Fresnel specification. Fresnel is a Fourier transform of is an F-spline, and we get a better resolution. And these are the result, and our experiment is in progress. This is the input intensity, and these are the interleaved banner. We address the phase, and these are the method of retrieving phase. This is the detected holograms. This is basically a simulation. The experiment is in progress, and from this we can retrieve the Fresnel field. And finally, we can see that if you go with the conventional method, there is a fall in resolution, and we can see that there is an imperfection in the phase reconstruction. And if you go for compressive sensing, we can say that when you go for this iterative algorithm with a loss of information itself, we assume that we are able to get a better resolution. The ambient intensity and phase can be reconstructed with a very high accuracy. And next one is we have implemented this in complex wave retrieval method also, the compressive complex wave optimization. And this is an algorithmic approach, and I'm skipping all this. I'll just show the results. This is the object intensity and phase we used, intensity and phase. And when we go for the conventional method of complex wave retrieval, the phase is corrupted. And without any sparsification, we implement compressive sensing, the phase resolution is better. When we incorporate a Haar wavelet sparsification, the results are even better. And an optimal wavelet, which is like a Fresnel is used, the results are the best we found. And we have done that in experiment. We have used this for characterizing the micro lens, and these are the This is with the conventional method. This is with the Haar wavelet sparsification, and this is with the Fresnel sparsification. These are experimental results we obtained, and this is the profile. And this is the way we characterize the micro lens. And thank you. If you have any question, please feel free to ask.
Thank you, Aneth. Any questions, please? Yeah. Okay. Thank you, Aneth. So we will move to the next speaker, Madhusudan Joshi. Dr. Madhusudan Joshi. Yeah.
Yes, sir. I'm there, but you have to give me the permission to share.
Okay. What is your login name? I'm not seeing you. Yeah, I see that. I see that. Yeah. No, you are. I think you must have used some other name. Achha, just Dr. Joshi. Yeah. Okay, you should be able to see now.
Yes. Is it visible now?
Yeah. Go ahead. Thank you.
Okay, thank you. So good evening to all the attendees, and this is just a little bit, some photographs of my institute where I work, called International Center for Automotive Technology. And I had done my PhD under Professor Kehar Singh and Professor Chandrasekhar from Applied Optics Lab, IIT Delhi. And on this occasion, I would like to first of all wish a very happy 80th birthday to you, sir, and a very healthy life ahead from my entire family. And I wish to thank all the organizers for giving this opportunity to me to make a short presentation about my work. And also, after almost a decade, it was really fun to see the signature representations from Applied Optics Lab, all those photographs which we have been using in our research papers, and all those MATLAB simulations. So it has been now a long time for me because now the area of work has totally changed. So I move on to the next slide. These are the contents of my presentation. A little bit about my institute, and then whatever R&D activities we have been carrying out, the publications and intellectual properties, and about small introduction about ICC, because that may be useful for entire IIT fraternity to know about this ICC concept, and then I would like to conclude. So We actually are known as International Center for Automotive Technology, and we are a national agency under Government of India for certifying, validating, design development, and doing a lot of work on automotives primarily. That is the mandate. We were established. We are fairly new organization, started in 2006 with about about 600 people, odd people working with us. Fairly young organization with average age of the employees about 32 years, and we are just 38 kilometers away from the international airport in Delhi, and located in Manesar with two campuses of 8 and 46.6 acres respectively. So this is an organization we are under Ministry of Heavy Industries and Public Enterprises, set up in 2006 with an investment of 1350 crore rupees by Government of India. This is the overall organization structure of the institute. We are, having so many laboratories, out of which I look after electrical electronics department, where we have 4 laboratories: electrical electronics lab, alternate fuel lab, electromagnetic compatibility facility, and the optics lab. So these are the area of interest, because nowadays automotives is rapidly changing with a lot of intelligent vehicles coming. So work areas are on cyber security and functional safety, intelligent lighting, intelligent transportation system, electric mobility, and of course a lot of data analytics and machine learning is also getting of more interest now because of more of connectivity coming into the vehicles. So these are the major responsibilities. We are a team of about 65 people, and you can see this is the photograph of the electromagnetic compatibility facility. To the best of my knowledge, it is India's largest EMC facility with a 30-meter chamber. Similarly, the optics lab, the photometry lab at ICAT is fairly large, and I think it's largest in India, because we have recently, also started doing, validation of general lighting. So the size has become very big. And then we are also the largest facility for validating the electric vehicles, starting from the components to the full-fledged vehicles up to heavy commercial vehicles and buses. So these are the services which we offer. We test electric vehicles, autonomous vehicles. We work on shared mobility, connected vehicles. As far as non-automotive are concerned, we are also, certifying, testing, and validating medical devices, IT devices, defense products, railways. And these are the major services being offered. We work towards standardization, validation, certification, research and development, and offer consultancy. And of course, lighting is always there, whether it is general or automotive. So this is a future trend of the vehicles. The coming years, you're going to see the vehicles of this kind. Those are called intelligent vehicles, and we can classify this technology into Ks, which means connected cars, autonomous vehicles, electric mobility, and shared. So starting from electrification, this is not a new thing. All of us are aware, reading a lot of news, a lot of articles, a lot of information about electric mobility nowadays is a new normal. But as far as connectivity is concerned, the connectivity will lead the automotive to become a kind of a, you say the complete, computer. You might have seen cars with a logo called Internet inside. So it's going to turn into a Internet IoT kind of a thing, where you can exchange information with outside world. Similarly, the shared mobility, the car will no more be a car, it will become rather a service. It may so happen that you drive your car for the whole day, and the surplus energy you store in the batteries, you can power your household while you come back in the evening. So these are not far off. We have seen certain concepts like this in various symposiums and seminars which I have been attending. Then last but not least, the autonomous driving, where these are driverless cars, and you may also think of a situation like IT in India is offering services to an entire world. Similarly, a person sitting in India is driving a car in US. A taxi in US is not not far away, and you can see this happening in reality in years to come. So we are also trying to catch up with this, what is happening around the world. So there are some national and international representations which I do, starting from standardization, leading some committees on ITS, Intelligent Transportation System, electric mobility, and also recently started working on a committee on drones, which is TD14 in the Bureau of Indian Standards. So I lead this panel. Then, almost taking active participation in automotive industry standard panels. Then as far as harmonization process is concerned, so we are trying to harmonize our regulations and standard to international standards. So I have been representing Indian delegation and rather now head of the delegation to Working Party 29, which is Working Party on Electricals at United Nations since 2007. And then also a permanent member and head of delegation to ISO TC 204 committee, which happens to be the Working Party on Intelligent Transportation System, and working very closely with Society of Automotive Engineers. As far as the responsibilities from the ministerial level are concerned, I am actually a permanent member of the task force on ITS with Niti Aayog, and also heading the panel on regulatory affairs for this task force, and also working very closely with Ministry of Heavy Industries to set up framework for faster adoption of electric mobility. So as far as the product development and R&D activities are concerned, we have worked on some of the topics which are actually of applied research, which are say dynamic headlighting system to solve the trade-off between glare and visibility on the roads while night driving. Then anti-glare headlights, intelligent speed adaptation system. I will describe briefly about these. Then we are also working on electric vehicle development. So most of the projects are aimed to lead to a commercial product. And then also an adaptive front lighting system. So far, working on different projects, funded projects of having value more than 25 crores, produced 12 patents and copyrights. So this is the first thing I would like to present about the dynamic headlighting system. This problem actually came to our mind while working, doing some analysis in the photometry lab at ICAT. So this is a typical headlight beam from a car. And if you try to draw ISO candela or ISOlux diagram for a typical headlight beam, it is like this, and the intensity at the center is highest, and then intensity, gradually decreases as you go out. And most of the headlights are basically over-designed, so a lot of unwanted intensity is available at the central part. So what we thought of that and this is a typical design of a headlight where we have the light source at the focal point of the parabola. So we thought of that if we can dynamically, displace this light center about the focus, say for a few millimeters or so, then we can try to, optimize the distribution of light intensity. So rather than having the maximum intensity, which is actually kind of too high.
Dr. Joshi, please finish in 1 minute.
Okay, so we can have a distribution of light around. So that is how it happened, and we developed a commercial product which was patented, and this paper was presented in Technical University of Darmstadt in one of the symposium, and this is a product which is available and is being licensed to people at a cost of 5,000 rupees. Similarly, this is a work which we have done an adaptive front lighting system where you can have beam shaping for the headlights by making a projector module, and this is a prototype which is being developed by ICAT, and we have filed 2 patents on it. This is the work which is done on the anti-glare headlighting system, for which some papers have been presented and 2 patents have been filed. So you can see a remarkable reduction in the glare coming from the headlights of the car. Then this is one work which we have done on electric vehicle development, where we have developed a prismatic cell, which is lithium-ion cell. As you may be knowing that in India still there is no production of lithium-ion cells. So we have done this work internally and produced this cell successfully, and we will be soon going for the commercialization of this. During a project, we have produced our own motor, which is a very, very typical example of a cylindrical motor of high performance, which has been used to convert a existing SUV Mahindra Scorpio into a hybrid electric vehicle, where the entire motor design, finite element analysis, computational fluid dynamics, and the entire design of the rotor, etc., has been done at ICAT. And this is a controller which was being outsourced to a company in Bangalore. Then this is the actual running motor which is fitted on the Mahindra Scorpio, and the price of this commercial kit is about 1 lakh rupees for a typical Scorpio without battery. So this entire work of design and development of this motor has been done at ICAT. The fabrication has been licensed to Kirloskar Electric in Hubli in Bangalore. So we have filed 5 patents, including the mounting, because this mounting is also special, as you may be seeing that this is mounted on the propeller shaft. So the propeller shaft has been removed, original one, and instead of that we have put the motor. So this design was special in terms of heat dissipation challenges, etc. So this work has been done, this challenging work has been done by the team at ICAT, and this product is available commercially now. Second, next product is what we have done is a commercial.
Can you please finish, Dr. Joshi?
I'll just give me 1 minute. So this is a intelligent speed adaptation system where we use GPS based mapping to control the speed of the vehicle automatically. So there is no need to manually control the speed. And this device is quite useful and is commercially available at the price of 3,500 rupees per kit. And this is a work which we are doing as a CSR activity where we are trying to develop an emergency braking system, which is a low-cost emergency braking system for the trucks which actually run into the cars, especially during night driving. So this is just a proof of concept which we have just done, and we are on the working on developing a commercial prototype for this, and this is actually being done as a CSR activity, as I mentioned, and this will be ultimately, given to the Ministry of Transport to make a mandatory fitment for the trucks, so that no such harsh accidents happen during night. So this is just a glimpse of the publications, and just a few more seconds, sir. Then I would like to tell that whenever there is a need, we don't have a very big conventional facility at in Delhi NCR. So ICAT has come up with a big conventional facility. We have a NCR's largest auditorium with 835 seats, and another auditorium with 400 seats, and then 6 parallel conference halls. So whenever there is a need for any event from IIT side, they can also try to utilize this facility, which is a national facility available for people to use. So these are the various events we have been organizing, and some of these events are quite big, like New Gen Mobility Summit. And this I would like to conclude. So applied research is being carried out at Electrical Electronics Department at ICAT on electric mobility, intelligent transportation system, and automotive lighting. And we are also playing a critical role in policy and rule making. Thank you so much, and thanks for having me here.
Okay, thank you, Dr. Joshi.
Sir, I have one question.
Yes, please click on.
Joshi ji, good to talk to you after a long time.
Hi. Hello, Rakesh.
Yeah, my question, what is the Light Symposium?
This is a symposium which we have been organizing since 2009, and we have already completed 7 editions of it. And this year we were supposed to have it, but I don't know. I'm not sure whether we'll have it this year or not.
So if not, for industry or industries or also for academia?
It can be for both. It is most of the academy is also attending this event.
Okay, so thank you, Dr. Joshi. So we should move to the next speaker, Dr. Bhargav Das from CSU Chandigarh.
Hello, sir. Am I audible?
Yes. Dr. Joshi, can you please unshare?
Yes, I unshare.
Yeah. Okay.
So, sir, can you see my?
No, not yet. Not yet. Okay, done.
You can see right now, sir.
Yes, yes.
And it's full screen also.
Yeah.
Yeah.
Okay. Yeah. So, good evening to all of you. I am Bhargav Das, currently working as a scientist at CSO Chandigarh. And on the onset, I'd like to congratulate sir on his 80th birthday, and also wish him all the good health and happiness for the coming years. So quickly going to the presentation, the topic of my presentation is interferometric introduction of 5 phase shifted FBG sensors. So pi phase shifted sensors are being currently explored by different research groups all over the world for high resolution measurement of dynamic strength because of its various applications such as hydrophones. Hydrophones are basically underwater acoustic sensors. They are also used for underwater military surveillance such as fiber optic passive sonar and marine monitoring. These kind of sensors are also used for ultrasonic detectors for medical sensing, acoustic emission studies, structural health monitoring and crack identification, and seismic monitoring for earthquake as well as ground vibration based surveillance. So there's a simple difference between a normal FBG, conventional FBG, and a pi phase shifted FBG. There's a phase shift element. Sorry. There's a phase shift element here. The phase shift element can be the phase shift can vary. It can be pi by 2 pi or 3 pi by 2, and the phase shift region can be anywhere within the grating. But mostly pi phase shift, which is at the center of the grating, are used for sensing applications because of its transmission spectra characteristics. So here I am showing the simulated spectra of a pi phase shifted FBG of 25 mm length with refractive index modulation of approximately 1.5 into 10 to the power minus 4. So if you see the top blue curve here, this is the transmission spectra, and within that transmission spectra we see a very sharp transmission peak, and the transmission peak is shown next to it, which is around of the order of the FWHM is of the order of 10 micrometer. So in sensing applications, the movement of this transmission peak is measured, and in contrary to a normal FBG, when in the lower figure I am showing the spectra. So the FWHM is almost of the order of 1 order magnitude lower than normal FBG, and similar to normal FBGs, the pi phase shifted FBG transmission spectra also follows the grating equation. So when the sensor is used for dynamic strength perturbation modulation, the transmission spectra modulates accordingly. But the challenge is the measurement of this high transmission peak. There are conventional FBG sensors already commercially available, but they are not suitable for measurement of this pi FBG transmission peak because of the resolution limitations. We can use an OSA, that is optical spectrum analyzer, but optical spectrum analyzers are basically static measurement because they are not there. First of all, they are very bulky, and their measurement speed is very slow. So one needs a special kind of technique for measuring the Bragg wavelength shifts in case of pi FBG sensors. So here for this we have proposed this concept of using a fiber-based interferometer. The fiber interferometer is a very high resolution interrogator for pi FBG sensors. It uses an unbalanced fiber interferometer and which converts the Bragg wavelength shift into a phase shift. So when light goes through the fiber interferometer, the wavelength shift is converted into phase shift, and which is measured with the help of a photodetector through a detector and then processed. Here, one thing we have to keep in mind that the path length, that is OPT, should be less than the. It should maintain the coherence limitations. It should not be more than the coherence length of the light source. So this is the simple interferometric equation. You can see almost everybody is known to this equation. So the Bragg wavelength shift, which leads to the phase shift and finally results into the change in wavelength. And the Bragg wavelength modulation of the pi-shifted FBG sensor peak wavelength is measured through this process. And if you consider the dynamic strength modulation of the pi FBG sensor peak with respect to wavelength as this, suppose if you consider simple sinusoidal modulation with an angular frequency of omega, the phase shift also modulates, and accordingly it is measured. So we have realized this concept experimentally. For that we are using a pi FBG sensor of length approximately 2.5 centimeter. The AC light when first goes through the pi FBG sensor, and the pi FBG sensor spectra can be seen as this one on the left side. So we are interested only in this peak. So for that, we are using an ABG filter, which is of the length of around 10 centimeter. So when it goes through that ABG filter, what we get, and this is the middle figure is the spectra of the filter. And when it goes through the filter, what we get is only the central peak, and which is used for the measurement applications. So initially we constructed or we fabricated a Mach-Zehnder interferometer using two 2x2 couplers and maintaining the part difference in such a way that it is lower than the coherence length. So this shows the interference pattern measured with respect to wavelength, and if you calculate the wavelength, path length difference, it comes out to be around 3.6 centimeter, which is lower than the coherence length, so there is no issue. So then we have put up this experimental configuration where the PIBG sensor is optically bonded into a cantilever plate, and we have placed a speaker on top of it so that the sound signal coming from the speaker generates strength modulations within the cantilever, and then the light, after going through the filter, goes through the interferometer to the photodetector to the DAQ, and the data is processed through LabVIEW and its frequency spectra is measured. So here we are showing a couple of experimental results. The left lower figure is the time signal recorded with the help of LabVIEW, and then if we observe the frequency spectra, we see peaks corresponding to the applied acoustic signal. Here the blue figure is for 580 for a single frequency, that is 580 hertz. And then we are also considering, we are also demonstrating, if we apply 3 different frequencies, and then those are also detected or sensed as per their frequencies. So overall, we have demonstrated a new concept for Bragg wavelet shift of PIBG sensors through interferometric concepts. The perturbation induced by dynamic modulation of the narrow transmission peak is monitored by unbalanced fiber interferometer, which acts as a wavelength discriminator. The smaller bandwidth of the narrow peak of the PIBG sensor gives us longer OPD, and longer OPD is beneficial for higher sensitivity. And this demonstrated concept is much simpler as compared to PDH and other tunable filter-based techniques. So this is the end. Thank you so much.
Okay, thank you, Dr. Bhargav Das. Any questions, please?
Yeah, I'm Senthil here. Senthil from SAC.
Okay.
Yeah, anyhow, first I wish our Professor Kehar Singh for his 80th birthday. Then I have a question to, I think, this CS scientist. See, that he was telling about that Ipson, that commercially available Ipson cannot probe 1 picometer kind of thing, but whereas we could do it statistically by averaging and taking the standard deviations, we could achieve that kind of numbers using the Ipson integrator. Though it's interesting to know that whatever that unbalanced Mach-Zehnder interferometer, however, we could do it. That is the point I want to tell to him.
Yeah, so basically, before even the interrogator can measure shifts, but before even it can measure, it has to detect the peak, because the concept, the interrogation concepts depends on first detection the peak. So for this kind of interferometers, you have to give FBGs with FWHM of the order of around 100 or 200 picometers. So if you give some light with with FWHM of 10 or 20 picometers, so initially it will not detect any peak. So if it doesn't detect any peak, then it will not be able to track the peak. So that is how we observe. But it can measure lower than the picometer range. But unless and until it can detect the peak, it will not process. Algorithm will not run.
Okay, thank you so much. This is the point I want to put. Thank you, Professor Joby. I'm Senthil from SAC.
Thank you. Okay, I think we can move to the last speaker, and we have. Thank you, Bhargav. You can unshare the screen. And next we have Dr. Poonam Arora from NPL, who did the MTech project with Professor Kehar Singh, and now she works in NPL to do the timekeeping of our Indian standards. Thank you. Please go ahead, Dr. Pune.
Good evening, everyone. Thank you very much, sir. I would like to thank Joby sir, Anurag sir, Professor Renu John, and Professor Naveen Nishal for organizing this symposium and also for giving me the opportunity to speak at the symposium. Am I visible, sir? Can you see my
Yes, very well. Yeah.
Full screen mode. Okay. All right. So I'm Poonam Arora from CSI National Physical Laboratory, and the title of my talk is Optics and Photonics for Precision Timekeeping. So at the outset, I would like to wish Professor Kehar Singh sir on his 80th birthday. That is why we all are here, and it's such a wonderful opportunity. We're delighted to see you, sir, in good health and still keeping active. May you continue to inspire us and future generations of photonics professionals, and I wish you good health, happiness, and active years ahead. Thank you very much, sir. Okay, coming to the topic. So I'm going to talk about precision timekeeping. So timekeeping has improved a lot. So we have come a long way from sundials to atomic clocks. So the quality of any clock depends on the kind of ticks it produces, which is basically the oscillator, which is the heart of a clock. So these oscillators have been changing, and that is improving the timekeeping accuracy over the last few centuries. So we have come from rotation of Earth, which is the natural oscillator that we have in the form of sundials. We had the timekeeping, then came the mechanical clocks. Quartz, of course, we are still using, but the latest generation is the atomic clocks, where an external oscillator is locked onto the atomic transition. And it's kept locked like that. So the oscillator output is as stable and as accurate as the atomic transition. And this is the concept of atomic time. And this is the field where 9 orders of magnitude improvement has been seen in last 100 years with more than 10 Nobel Prizes. And of course, most of the technologies which have been enabling the precision timekeeping are optical technologies. And that is why I chose this topic to present today. So I'm going to present the basic idea and some of our work on the atomic clocks that we do at NPL. The kind of improvement that has happened in timekeeping accuracy is clear from this graph. You can see over last many centuries, the timekeeping accuracies have been improving. And you can see the clock which loses 1 second in 1 minute to optical clocks which lose 1 second in the age of the whole universe. So we have come a long way, and there is still way to go. We are in all optical domain. We are moving towards the optical second, and even nuclear clocks are being talked out. But nevertheless, optical technology is the backbone of all these improvements. So in the middle of the last century, about 1967, the SI definition of 1 second was defined on the base of hyperfine transition frequency of 9192631770 Hertz in hyperfine levels of cesium-133 atom. And since then, we are living in the atomic time, and the whole timekeeping in the entire world is being done on the basis of cesium clocks. So this is the beginning. In the year 1955, NPL UK was the first one to come up with a cesium atomic clock. So this big instrument that you see is the cesium atomic clock. So what goes inside a cesium clock is the cesium atoms produce the atomic beam in an oven, and then the beam comes out, and the atoms interact with the Ramsey microwave cavity, because the transition in the cesium atom, which is 9.1 gigahertz, is the microwave frequency. And at the end, the atoms, after the interaction with the microwaves, are detected for the change in their state, and an external quartz oscillator is locked onto the atomic transition frequency. And of course, there are many other components which make the whole clock work possible. So the clock technology has improved a lot, and these days it's available in a tabletop system, which you can see like this. It's about like 1 meter by 1 meter size square box, and it's quite reliable technology, and these are the workhorses for the worldwide timekeeping. And the accuracies of the order of part in 10 to 13. So these are extremely stable and accurate timepieces. So modern era of atomic clocks, we can divide in 2 parts, microwave clocks and optical clocks. So in the microwave clock, of course, I showed you the cesium beam clock. They're called beam clock because the cesium beam is being used for interrogation here. And the accuracy, I said, 1 order in 10 to 13. The next version of the cesium clock, which is much more accurate, almost 3 orders of magnitude more accurate. And this is called a cesium fountain, which employs the technology of laser cooling and magneto-optical trapping. The cesium atoms from the vapor state are cooled and trapped. and launched up through the microwave cavity. And as they fall back under gravity, excuse me. So as they fall under gravity, they are detected for the change in their state. So that is how a cesium fountain works. And this is the primary standard, because the primary standard is one which realizes SI second with the highest accuracy. So this is the current primary standard of atomic time. In the future of timekeeping are atomic clocks, and the work has already started. So there are two ways to realize an optical clock. One is trapping neutral atoms in an optical lattice. And the other way is to trap a single ion and then probe its optical transition. So the difference is here in the microwave clocks, we are probing the microwave transitions, and in the optical clocks, we are probing the optical transition. And in a few slides, I'll show you why and how the improvement in accuracy comes from improvement in the frequency. The higher the frequency, the better the accuracy. So at CSR NPL, we are engaged in R&D on development of atomic clocks, and we have already successfully developed one cesium fountain clock, and we are already developing a second cesium fountain clock to improve upon some of the issues that we faced with the first fountain clock. And recently we have started building the first optical clock also for India, which is based on single trap ytterbium ion. So I'll quickly go through some of our results on the cesium fountain clock. So a fountain clock consists of broadly three parts: the control electronics, physics package, and the optical setup. So this is the physics package. This is the layout of the physics package of the cesium fountain at NPL that we have. So this gray shaded region is the ultra high vacuum. This is the magneto-optical trap, where all the laser beams come. So 4 in the horizontal plane and 2 in the vertical plane. And the cesium atoms are cooled, and then they're launched through the microwave cavity up. And then after achieving the toss height, they fall back under gravity. And this is the detection zone where the atoms are detected for their state, and a transition probability is calculated. So this is a closer look of the magneto-optical trap that we have. So this is the detection zone and the magneto-optical trap at the bottom. This is the optical setup. So of course, optical technology is at the heart of improvement in timekeeping accuracy. So this is the detailed optical setup. We have a master laser. We derive 8 beams from the master laser, and of course there are lots of frequency shifting elements, acousto-optical modulators. And then we have a repump laser, because while going in the cooling cycle, sometimes the atoms drop to the lower state. So a little amount of repump is required to bring the atoms back in the cooling transition. The repump laser is mixed with one of the cooling beams and in one of the detection beams. So a simplified optical setup looks like. So at the end, we have 8 beams derived out of the 2 lasers. And of course, another thing to point out is these lasers are frequency stabilized external cavity diode lasers. And this is the close-up view of the optical setup that we have for the first fountain. And this is the characterization of the magneto-optical trap. So the bright spot at the center you see are the cold atoms trapped. So these are about 10 million cesium atoms. The temperature immediately after Doppler cooling is about 125 microkelvin. And of course, this is not enough for the fountain to operate. So we need to apply post-cooling techniques. And then we get down to about 6 microkelvin temperature. So this is the typical fountain cycle where we cool trap the atoms, launch them through the microwave cavity, and of course a second stage cooling is applied. A state selection, because only one kind of atoms are allowed to go for Ramsey interaction. Ramsey interaction is the interaction in the microwave cavity, and the typical interaction technique is named after the scientist Professor Norman Ramsey. And then the atoms are detected in the detection zone, and the whole cycle continues. So one cycle gives us 1 point measurement of the transition probability that you see here. So at the lower end, left side, you see the Ramsey fringes, which is the typical feature of a cesium atomic fountain. And this is the counterpart of Young's double slit experiment, which gives the fringes in the spatial domain. And here we see the fringes in the temporal domain. And the accuracy of the cesium fountain is part in 10 to 13 at 1 second. And as we approach the averaging time of about 1 day, so it reaches part in 10 to 15 accuracy, which is amazing. The best fountain in the world goes an order better, which is 10 to minus 16. But nevertheless, we could achieve this much stability with the first fountain. So to improve...
Dr. Graham.
Sir, I'll quickly finish. Yes, sir. So the first fountain was already approved as a primary frequency standard, which was a proud moment for NPL. And then we wanted to improve on the accuracy, so we are designing the second cesium fountain, employed some new techniques, optical pumping to improve the signal to noise ratio. Again, lot of optical technologies are making things better here for us again. And we have lots of indigenous components like beam expanders, viewports and all that we have designed ourselves. And this is the fountain setup. So what we have done for the optical setup of the second fountain, we are removing the free optics geometry and we are going for all fiber geometry in the second fountain. So now coming to going from microwave to optical clocks. So the noise in the clocks, it reduces as proportional to the square root of the total number of atoms that are trapped, and also it's inversely proportional to the frequency of transition. So that's why going from 10 to 10 hertz in micro transition to 10 to 14 hertz in optical transition gives us an edge, and we expect an improvement in the total accuracy and the noise reduces. And that is why people are moving from the microwave second to optical second. So as I already said, there are two ways: a single trapped ion or neutral atoms trapped in optical lattice, and people are working, the groups are working in both the technologies. So just a demonstration of trapped ion clock. So a single ion is trapped in a quadrupole Paul trap, where an oscillating electric field traps the ion, and laser cooling is used to cool the atoms, and the fluorescence imaging is used to probe the fluorescence after employing the clock probing beam on the ion, and the transition probability is calculated. So such ion clocks are accurate to 1 order in 10 to 17. So development of trapped ion clock, definitely it's an optical clock, uses lots of optical technologies. So a Paul trap or a quadrupole trap is used to trap the ion. Then lasers are used for cooling and trapping of the single ion. Then the ultra stable probe laser is required, so ULE cavity is required for the probing, and the whole instrument needs to be operated as a frequency standard. And for the evaluation of frequency, comp is required. So you can see the intense use of optical technologies in optical clock, as the name suggests. So another requirement of optical technology is the comparison of optical clocks, because a standalone clock in a lab doesn't mean anything unless we compare clocks over continents. So over continents, people are trying with noise compensated stabilized optical fiber links, but there are still some issues. There are new optical technologies being used for precision time and frequency transfer, which are like all optical two-way time transfer and part optical and microwave links. So there is a long way to go, and optical technologies are enabling all the progress in this field. So why precision timekeeping? There are lots of requirements of precision timekeepings. All the architectures are moving on digital platforms, and some applications like navigation, financial services, smart grid, space, all these applications rely heavily on precision time. And apart from this, scientific curiosity is also driving the research in this field. So we want to see how constant are constants of nature, and that's how the technology is moving to part in 10 to 18 kind of accuracy evaluation. So one such application in the navigation, so trilateration principle is used for navigation, how you identify or pinpoint the position. So 3 satellites have to be there in sight. So you get the arc of the wavefront from one satellite, a similar arc from the other satellite. So you can be either here or here, and then you need a third satellite, and then you can pinpoint and find out the position very accurately. So there are atomic clocks on board all the satellites, and a synchronization error on clocks between the satellites of 10 nanoseconds error will lead to position error of 3 meters. So satellite clocks need to be precisely synchronized to few nanoseconds. So all the Google navigation that we use these days heavily relies on the atomic clock technology. So in conclusion, I would like to say that we are moving towards accurate timekeeping. We are moving from microwave to optical second. In a few years or maybe in a decade, the SI definition of 1 second will change from the microwave definition based on cesium atom to some optical transition in one of the elements, which could be ytterbium, strontium, and the technique can also be decided in coming years, whether it will be ion trap or optical lattices. It's an amazing area of research and lots of optical technologies enabling, and you can appreciate 10 to minus 15 accuracy is like measuring the distance between Earth and Sun with an accuracy of 0.1 mm. And minus 18 accuracy is like optical clock will not lose or gain 1 second over the age of universe. So that's how amazing these technologies are. So I'd like to acknowledge all the previous students, colleagues, Professor Sen Gupta, the ex-head, and all the support from funding agencies. So to all of you for being the patient listeners, thank you very much. And thank you again, Joby sir, for giving me the opportunity.
Thank you, Poonam, for your nice talk. So, any questions? Yes, we have.
Can you hear me?
Yes.
Yes.
Okay, so I just have a quick question. This is great work. I'm familiar with clock work because I'm involved in clock research. So I just wanted to know what kind of noise is limiting the frequency stability of the fountain clock that we are building now.
Yeah, so a fountain as such one can improve by reducing the line width. So line width is the time spent of the atoms interacting with the microwaves. So you can reduce the line width to an extent until unless it is restricted by the quantum projection noise. So quantum projection noise is limiting the stability. So that is how we are not able to improve the accuracy with the current cesium technology. And we are moving to optical technology because we are increasing the frequency there.
So this is close to the projection noise limit, the stability that you're getting?
No, right now the cesium fountain is not limited by the quantum projection noise. We have other systematic effects which are still limiting. The stray magnetic fields are there which are restricting the temperature of the atomic cloud to go down. But the best fountain in the world, which is right now in NIST USA, so they have the performance of the fountain which is limited by the quantum projection noise.
Poonam, I have a question.
Yes, sir.
How many of these components which you have used on optical table are really made in India?
Good question,
is a simple question because I really want to know technologically where we are.
Yeah.
Scientifically, we are very good.
Yeah, so it's all indigenous assembly of the equipment, but of course optics we have bought mostly from outside, but we do some small instrumentation. For example, the locking circuit, the analog locking circuit of the laser was with the photodiode amplifiers.
About optics, nothing about, because how many components, because I have heard the whole talk from morning to evening, and I have never seen anybody talking about optical instrumentation. Anything which is being done in the country, people have used very nice, big, huge equipment. My concern is that unless we do things which can generate money for the country, we are still the developing nation. Scientifically, we may be very good, but industrially, we are not really as good. That is the point I want to raise through this one. I want some people to really get involved in doing things which generate money for the country.
Yes, absolutely. We are trying to do a lot of small
Kehar Singh is laughing because I have been trying this from last 80 years. I was born along with him. Okay, so anyway, Poonam, thank you very much. It's a good work. And thank you to everyone else. I really enjoyed, learned quite a few things, but I am unhappy because we are not generating money for the country.
Thank you. Thank you, sir. We have a question from Dr. Pradeep.
Yeah, Dr. Poonam, do you have any program on rubidium clocks?
Yeah, so on rubidium clocks, we used to have one program for SAC Ahmedabad, ISRO. We were developing the physics package for the rubidium clock because rubidium clocks are used for satellite payloads. So we developed it for some time, and then we even had the cells and bulb filling for rubidium. But this was a project, it was a sponsored project from ISRO, but after the project got over, right now we are not doing any development of rubidium clocks, but we are using rubidium clocks for GPS disciplined oscillators, but these are commercial rubidium clocks.
Because the previous speaker just now who was talking, I don't know the name, he was telling about the money generation for the country. I think if we get a good rubidium clock which is indigenously developed, it will be a good thing for Indian program, Indian IRNS programs.
Yeah. So SAT Ahmedabad is already developing rubidium clock. So I know a person there, Dr. Tejesh Bandi. He is leading the group, and rubidium clock is being developed. And initially, the work for the physics package development was done long back by NPL also. But we have limited manpower at NPL, so right now we are not engaged in R&D on rubidium clocks. But maybe in future we can think on even chip scale atomic clocks for that matter.
Okay, thank you.
We have a question from Dr. Sriram.
Yeah,
Sriram.
Yeah, we can hear you.
Dr. Poonam,
yes,
for this nice presentation. My first question is, when you talk about this, the so-called Allen deviation.
Yes.
Is it for short-term stability or long-term stability?
For both. So Allen deviations are normally
specifically the number 10 power minus 17 and all what you're planning for this trapped ion system.
Yes.
So is it long-term stability?
Yes, that's the long term. So at 1 second or at 10 second that you see is like a short-term stability, or even up to a day. But what you get more than day of integration time is the long-term stability.
Right.
So that's the long-term stability.
Another question: how do you rate this, quantum interference-based techniques like CPT for this purpose?
So CPT-based clocks are used for even chip-scale atomic clocks and even for rubidium clocks. So there we are using CPT scheme, but not for fountains. There we are not employing, and even for the optic clocks, we are not using CPT-based technology. But for rubidium clocks, yes. For atomic chip-scale atomic clocks, we do use CPT.
No, in terms of its stability criterion, how do you foresee that development?
Development of CPT-based rubidium clocks, you mean to ask?
Right.
Yeah, so they are. It's a very time-tested technology. For chip-scale atomic clocks, definitely people go for CPT-based clocks. So there, you have you can do a vapor cell-based clocks, or you can have a micro trap on a chip. Both use CPT-based technologies. So there, the stability is not that much of concern. But for a primary standard, the SI definition of second is based on cesium. So you have to work with cesium. So there we don't.
Very recently, I came across one more in literature called paper clocks.
Yes.
In the sense, many clocks are stationed in a navic constellation.
Yes.
So wherein they talk to each other, and then you get a better stability.
Yeah, so if you have a synchronized system, so you don't have to employ a very high end clock, like a cesium clock is a very expensive one. So you can, indigenously develop your vapor cell based clock. So from point to point, and for IRNSs or for NAVIC, I know they have many ground stations. So sometimes they use their own indigenously developed vapor cell clocks. So that can be.
In terms of miniaturization, which is the most feasible, technique?
For miniaturization, of course, the chip-scale atomic clocks. NIST has already developed. There was some work being done at RRCAT in Indore, but at NPL we don't have. Up to now, we don't have this activity. We have not started yet. But maybe in future we would like to take this up.
Right, ma'am. Thanks.
Thank you, Dr. Poonam, and you can unshare your screen.
Yes, sure.
Thank you very much. So let's thank all the speakers. So we conclude the first part of the symposium, and thanking each and everyone. And we are quite late, of course, but I hope it was okay. We really enjoyed each and everyone. We enjoyed. So we can move to the next part. Should we take a break, sir, or what do we do?
No, I don't think.
I think, yeah.
After break, the reassembly will be, again, will take a lot of time, and people have joined because.
That's right. Yeah, absolutely correct.
People have joined for that purpose. So let's continue, and so we will now get into the a different mode. We were in scientific and engineering mode, not in technology mode, as Professor Sirohi says, but we are still in science and engineering mode, and now we move to to a social mode, and we look at Professor Kehar Singh's interaction with some of us on a different scale. So we have about 100 participants, so I don't think everybody can speak in this, but we'll try to see how many people can speak, and please keep your comments to if you have 4 or 5 things to say, you say just one of those, that's what I would say. Otherwise we'll be sitting at 12 o'clock in the night and that'll be too long. So we will plan to wrap up in 1.5 to 2 hours, not more than that. So at the end, Professor Kehar Singh will also speak, and I presume he will take a little longer. So we have limited time. So we will begin with some senior people, and then we'll go to in a little bit on seniority, and then you can raise your hand when after that. First I will call some people, and then you can raise your hands, and then I will see how we can accommodate different people, right? So first of all, I would say